Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Agung and my partner Rina is wonderful and precious chance for us to be your master of ceremony. In this beautiful morning, the 16th of November 2020.
Selamat pagi, salam sejahtera. Saya Rina dan rekan saya Agung. Sebuah kehormatan bagi kami menjadi Master of Ceremony pada kesempatan pagi hari ini, 16 November 2022.
The Honorable Rector of Universitas Jember, Dr. Insinyur Iwan Taruna MM.
Yang terhormat, Rektor Universitas Jember, Profesor Dr. Insinyur Iwan Taruna MM.
The Honorable Vice Rector 1 of Universitas Jember, Profesor Dr. Andes Slamin MPhil SG PhD.
Yang terhormat, Wakil Rektor 1 Universitas Jember, Profesor Dr. Andes Slamin MPhil SG PhD.
The Honorable Head of ICCGANT, Profesor Dr. Andes David MSc PhD.
Yang kami hormati Ketua ICCGANT, Profesor Dr. Andes David MSc PhD.
The Honorable Keynote Speaker of this event, and distinguished guests, ladies and gentlemen.
Yang kami hormati pembicara kunci pada seminar kali ini, serta hadirin sekalian yang berbahagia.
Welcome to the second day of the International Conference on Combinatorics, Graph Theory, and Network Topology 2022. Ladies and gentlemen, first of all, let's say thanks to Allah who has given us guidance, happiness, health, and well-being, so we can attend this event without any obstacle. Praise and salutation always upon our Prophet Muhammad Sallallahu Alaihi Wasallam.
Pertama-tama, marilah kita panjatkan puji syukur atas kehadiran Allah SWT, atas berkat dan rahmat-Nya lah kita dapat bersama-sama menghadiri acara ini tanpa ada kendala apapun. Sholawat beserta salam semoga selalu terpanjatkan kepada Nabi Muhammad SAW.
Ladies and gentlemen, we would like to begin with informing you about our today's agenda.
Hadirin yang kami muliakan, izinkan kami terlebih dahulu membacakan susunan agenda pada hari ini.
The first is opening session.
Acara pertama pembukaan.
The second is opening dance performance.
Dilanjutkan tari pembuka Nyambi Peltek.
And followed by singing national anthem of Indonesia.
Acara kedua menyanyikan lagu kebangsaan Indonesia Raya.
And the third is singing hymn of Universitas Jember.
Acara ketiga menyanyikan himne Universitas Jember.
Followed by opening speech by representations of keynote speaker.
Dan dilanjutkan sambutan keynote speaker.
Followed by opening remarks by head of ICCGANT.
Dan dilanjutkan sambutan dan doa dari Ketua ICCGANT.
The sixth is watching ICCGANT 2023 videos.
Acara selanjutnya penampilan video ICCGANT 2022.
Followed by presentation from our keynote speaker.
Acara selanjutnya presentasi dari keynote speaker.
The seventh is closing.
Dan acara ketujuh penutup.
The last but not least, the announcement and the panel sessions.
Acara ke-8 pengumuman dan sesi paralel.
Ladies and gentlemen, today at the sake of time, let us start our agenda today by reciting basmalah together.
Hadirin yang berbahagia, marilah kita buka acara ini dengan bacaan basmalah bersama-sama.
Bismillah. Ladies and gentlemen, step to the next agenda is opening dance by Sanggar Tari Hastari with Nyambi Poltek Dance.
Acara selanjutnya penampilan tari Sanggar Tari Hastarini Nyambi Peltek.
Ladies and gentlemen, please give applause for Sanggar Tari Hastarini.
berdepan. Berdepan.
Ladies and gentlemen, start to the following agenda, that is singing national anthem of Indonesia and hymn of University of Jember. So ladies and gentlemen, please stand up. Thank you.
Acara selanjutnya adalah menyanyikan lagu kebangsaan Indonesia Raya dan himne Universitas Jember. Hadirin mohon berdiri.
Thank you very much, ladies and gentlemen. Please take yours.
Hadirin disilakan duduk kembali.
Ladies and gentlemen, entering the next agenda is opening speech by the representations of the keynote speaker.
Kami persilakan sambutan keynote speaker Dr. M. Petakacacalam.
To Dr. M. Petakacalam, the floor is yours.
Good morning, all of you.
Hi. Good morning, sir. Professor Honorable Chairman of Research Group, Professor members, and the Dean of Sciences, University, that is Government State University, India. Very happy to stand before you all here. Since Professor Devi and our faculty members, this research group, they have published some books also. Recently, they are doing their application of the graph theory in agriculture area, and also they are doing research work in domination, labeling, coloring, and other areas. Really, I am very happy since in Indonesia, I think this is the very famous and fantastic research group in the area of graph theory, especially nowadays. They are trying to find the applications of the graph theory and applications of the graph coloring, especially now they found some new results in the domination number in the area of agriculture, and they are using some equipments under the project from the Ministry of Indonesia. And after the publication, we will come to know about their beautiful results. Okay, I think I request the Professor Devi, they apply for the patent for their new work in the area of agriculture. I hope after publishing their paper, many researchers in the area of applied mathematics, people in and around the world, definitely they will cite this paper for a trillion times, I think. And they are all the students, even in the undergraduate and postgraduate students, they are enthusiastically working in the research, and they are even in the postgraduate, they are trying to publish the papers in Scopus Index journals. I am really very happy since they are all dedicated for the research work. They are all dedicated for the research work. In this university, the early morning they reach to the university and research group. They are all discussing in the friendly manner, and the professor also they helping in all the students, and even in the other department students, biotechnology and other social science and computer science students also visiting this research group, and they are trying to work in the multidisciplinary manner. And also many professors from various countries, Australia, Turkey, and India, and various other countries, the speakers are regularly giving the guest lectures. And recently, in the last month, many professors from various countries delivered the guest lecture programs. Even myself and Mohana Priya from Combinatorics College, We delivered this lecture. All the students attended and asked many questions, and we discussed a lot. And even there after the conference, in the after lunch and in the free time, we are all discussing only about the graph theory and the research and the applications of the graph theory results in the area of some other areas like computer science and agriculture and digital. I am really very happy, and they are consecutively organizing the conference. Every year they are organizing the second conference. This is the 6th time consecutively without break. They are organizing the conference in very successful manner. This is the 6th one, and I hope they will organize regularly in year by year for the future also. And the speakers yesterday, Professor ICCGANT from Turkey, and delivered the talk, and myself and Professor Nefik also delivered the talk. Today we are waiting for the talk of Professor Lokesa, and after the Lokesa and some other speakers from Salamin from this university, that is Vice Rector, he will also go and deliver the talk. Once again I congratulate Professor Nefik and his team for organizing these type of wonderful conference. And once again, I thank the scholar students for supporting our Professor Nefik for organizing these type of wonderful conference. Thank you, Madam.
Thank you very much for the opening speech, Dr. M. Venkatachalam.
Terima kasih atas sambutan dari Dr. M. Venkatachalam.
Ladies and gentlemen, the next opening remarks is delivered by Head of ICCGANT, Professor Dr. Andes David, MSc PhD.
Dan selanjutnya sambutan oleh Ketua ICCGANT, Profesor Dr. Andes David, MSc PhD. Disilakan.
Professor David, the floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Alhamdulillah. Wa syukurillah. Alhamdulillah. Honorable Rector, the University of Jember, Honorable Deputy of Rector for Academic Affairs, Professor Andes Slamin, and MSc PhD, the honorable distinguished invited speaker from yesterday until now, Associate Professor Dr. Venkatachalam, Associate Professor Dr. M. Hanpriyan, as well as the special one, distinguished invited speaker who already in the Zoom meeting right now, Professor Dr. Lokesa. Good morning, Professor. And all the participants who are joining offline or online in the Zoom meeting for the 6th ICCGANT Conference 2020. As I mentioned before, that this conference aims to invite all the researchers or invited speakers who are working in combinatorics in graph, as well as in mathematics and applied mathematics, and gather together to share an idea about the new recent topic or recent result on that research of interest, namely combinatorics in graph and application. Today is the second day of the ICCGANT conference, Yesterday, there were some invited speakers have presented their research topic in many areas and many research of interest, such as labeling, coloring, domination, number of a graph, as well as the uh, application of the combinatorics and graph theory. But also becomes a main focus in this ICCGANT conference. Hopefully, in this second day, we will have a good discussion. Especially, we will hear the presentation of Professor Lokesa, the one who already having a joint research with ICCGANT research group as well. And we have already publication in a good reputable journal. For all the participants, all the other speakers, we are very much welcome to all of you to share your research results in this area of in mathematics application in general. And your papers will be selected by our reviewers. Once your papers are selected, then we will publish your paper in the proceeding or in the journal indexed by Scopus or WAS. Finally, I should say that hopefully this conference, the annual conference of ICCGANT, will be benefiting to all of you. By reciting Basmalah, Bismillahirrahmanirrahim, of the name of God, I formally open this second conference ICCGANT for all of you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Professor Dalin, for the remarks.
Kami ucapkan terima kasih atas sambutan Ketua ICCGANT, Profesor Dr. Andes David, MSc, PhD.
Ladies and gentlemen, we are entering the next agenda. That is already a prayer delivered by Zainul Rashid Ridho, SPD, MPD.
Acara selanjutnya adalah pembacaan doa oleh Bapak Zainul Rashid Ridho, SPD, MPD.
For Mr. Zainul, the floor is yours.
Kepada Bapak Zainul, disilakan.
Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Hamdan syakirin, hamdan na'imin, hamdan yuwafiqu ni'matahu mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalalika wa azimi sultanik. Allahumma shalli wa sallim ala sayyidina Muhammad wa ala ali sayyidina Muhammad kama shallaita ala sayyidina Ibrahim wa ala ali sayyidina Ibrahim fil alamin innaka Hamidum Majid. Allahumma inna nas'aluka salamatan fid din wa afiyatan fil jasadi وزيادة في العلم وبركة في الرزق وتوبة قبل الموت ورحمة عند الموت ومغفرة بعد الموت. اللهم هون علينا في سفرة الموت والنجاة من النار والعفاء عند الحساب. اللهم يسر لنا ولا تعسر. اللهم إنا نسألك علما نافعا ورزقا واسعا وشفاء من كل داء وسقام برحمتك يا أرحم الراحمين. يا الله يا رحمن يا رحيم يا مجيب السائلين. To you belong our praises, university, to reveal our hearts and our mind, so that we can receive useful knowledge about graph theory and network topology from this conference in second day of ICCGANT 2022. Please, Ya Allah, add our knowledge and our standing. برحمتك يا أرحم الراحمين. ربنا هب لنا من أزواجنا وذرياتنا قرة أعين واجعلنا للمتقين إماما. ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار وادخلنا الجنة مع الأبرار يا عزيز يا غفار يا رب العالمين. سبحان ربك رب العزة عما يصفون والسلام على المرسلين والحمد لله رب العالمين. والسلام عليكم ورحمة الله وبركاته.
Thank you very much to Mr. Zainul.
Kami sampaikan terima kasih kepada Bapak Zainul.
Ladies and gentlemen, we are now entering our main agenda. We will begin with watching ICCGANT 2022 video and followed by our plenary sessions by our keynote speaker.
Hadirin yang berbahagia, kita memasuki acara inti pada hari ini, yaitu penayangan video ICCGANT 2022 dan dilanjutkan dengan plenary session oleh pembicara tamu kita.
But before we started, we would like to introduce our speaker today, the Dr. P. Indonesia, PhD from Wijayanagara Sri Krishna, Devaraya Bala Indonesia.
Presentasi pertama disampaikan oleh Profesor Dr. P. Lokesha PhD dari Wijayanagara Sri Krishna Devaraya Balari, India.
And the second presentation will be delivered by Profesor Dr. Andes Islami MCom PhD from University of Jember, Indonesia.
Presentasi kedua akan disampaikan oleh Profesor Dr. Andes Islami MCom PhD dari Universitas Jember, Indonesia.
And the third presentations will be delivered by Kiki Ariyanti, MSc PhD from Universitas Indonesia.
Presentasi ketiga akan disampaikan oleh Kiki Ariyanti, MSc PhD dari Universitas Indonesia.
And the fourth presentations will be delivered by Anne Mohana Priya from Combinatorics Art and Science College, India.
Presentasi keempat akan disampaikan oleh Anne Mohana Priya dari Combinatorics Art and Science College, India.
And this plenary session will be moderated by Robiatul Adawiyah SPD MSc from Universitas Jember, Indonesia.
Dan sesi ini akan dimoderatori oleh Ibu Robiatul Adawiyah SPD MSc dari Universitas Jember.
Ladies and gentlemen, this is the second day of the sixth ICCGANT 2022.
Okay, well, ladies and gentlemen, may I have your big attention, please? Assalamualaikum warahmatullahi wabarakatuh. Swastiastu, Namo Buddhaya, salam kebajikan, rahayu. Good morning, ladies and gentlemen. I am Robia Tuladavia. I am as the moderator in the second day of this plenary session. I am very pleased to see you here and welcome all of you in the second day of ICCGANT 2022. Ladies and gentlemen, in the second day of plenary session, we have 4 invited speakers. The first is Professor Dr. P. Lokesha, PhD from Vijayanagara Sri Krishna Devaraya Ballari, India. And the second is Professor Slamin from the University of Jember. And the third is Dr. Kiki Arianti Sugeng, MSc from Universitas Indonesia. And the last is Dr. Mohana Priya from Combinatorics Art and Science College, India. Before we go on to the presentation of our invited speaker, let me read the regulation of this plenary session. Every speaker has about 1 hour. It consists of 45 minutes for presentation and 15 minutes for discussion. If the audience has a question, you can write the question in the chat box, or you can ask directly to the speakers by using the raise hand feature in the Zoom meeting. Let me call your name first, and then you can ask directly to the speaker. Now we go on to the first presentation of our first invited speaker, Professor Dr. P. Lokesha, PhD. Hello, Professor. Are you with us?
Yeah, good morning. Salam.
Can you hear my voice, Professor?
Yeah, ma'am. You? Are you hearing?
Okay, yes, but your voice is not, yeah, it's okay. But before we go on to your presentation, I'd like to read the short CV of Professor Dr. P. Lokesha, PhD. Professor Dr. P. Lokesha, PhD is a professor in the Department of Studies in Mathematics in Vijayanagara Sri Krishna Devaraya University. And his research interest is in functional analysis, graph theory, operator theory, and mathematical inequalities. He guides both 10 students and awarded, and 1 student in final thesis is submitted, and 7 PhD students are working. And Professor Dr. P. Lokesha, PhD has about 58 publications in the Scopus with H index 11. Okay, Professor Dr. Lokesha, PhD, time is yours.
Yeah. Good morning. Salam alaikum. Salam. And first of all, I would like to thank the Professor Dafiq. He is always he's a good friendship with me, almost 4 or 5 years. And he invited me to the 6th International Conference on Combinatorics, Graph Theory, and Networking Topology. Because many times he invited me to come to Indonesia, but I have a busy schedule related to administration work. That's why little troubled me to come to Indonesia. Maybe I will try to meet you, all of you, in the next conference in the this international conference. Is it visible, ma'am?
Yes, sir. It's very clear.
And also I thank all the organizing committee of the 6th International Conference of the Combinatorics, Graph Theory, and Network Topology, University of Jember, Indonesia. This is one of the good opportunity for the younger researchers, as well as the middle one, and all the other scientists. These type of conferences will be helpful to us for a one-to-one know each other and the younger researchers are presenting here. Many papers are publishing after the conference, after the review of the after presentation, the review process will be started and it will be published in a good journal. Already Professor Defik told about the this conference highlight. In this talk, I will suggested the investigation of graph invariant and its relevance. Here, the graph invariant is not a new concept. It is introduced in 1947 by Wiener. That is the first phase. After that, many graph invariants are introduced. In this concept, I thought that some of the basic concepts related to the graph invariant I will introduce here. And recently, we introduced, one of my students is introduced by. In my talk, I will discuss some of the important points. First, started with an introduction. What are some of the graph invariant and some of the operations related to graph invariant, and recently introduced graph invariant, how it is introduced by the background of the study and motivational works, and method of development of new graph invariants. And some of the softwares are also utilized for the purpose of checking the graph invariants, and some of the recent publications as well as books I highlighted in the last slides of my talk. Actually, the graph invariant and topological index is one and the same in the molecular graph theory. Generally, this graph invariants are more attracted by the mathematical and chemical literature. Plenty of graph invariants are introduced and extensively studied. And nowadays, almost 7,000 graph invariants are introduced. They are interrelated with the chemical analysis as well as mathematical concepts. Here, in this talk, I will mainly concentrating on the concept of one of the index recently introduced by one of my group student, that is Deepika T in chemical graph theory. It is degree-based graph invariant. She is motivated from the Zagreb indices. In 2021, after that graph invariant VL index is introduced, that is motivated by many researchers. That is one of them in the same group, research group, that is Suvarna and his team introduced the temperature index, VL temperature index, VL status index for graph structures. These two indices are well correlated with some of the butane structure. The graph invariants are used to quantitative structure activity relationship as well as quantitative structure property relationship studies. These are the simple abstract I given here. And now we can start with what is molecular topology. Suppose if you take a molecule M, that molecule can be composed into a different N atoms, that is A1, A2, etc. AN. Suppose if you take any two atoms, AI and AJ, we can decide what are the two statements. One of them is if the molecule M, there is a chemical bond between the one and the another. That is known as AI and AJ. There is a chemical bond between them. Otherwise, there is no chemical bond. These are the two simple concepts for the correctness. Then the totality of the information about the mutual connectedness of all the pair of atoms, that is known as molecule, determines the topology of the respective molecule. This is the basic definition. Now we can give one of the simple example, that is ethanol. Ethanol is, this is the ethanol, and representing the topology is described as follows. For convenience, we are mentioning here, this is circles, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. then that can be written in a graphical notation in the molecular graph of ethanol. Now we move on to a graph invariant. This is the basic structure, simple concept, how to calculate the graph invariant. Typically, we can say that adjacent vertices are some function such as root, square root, sometimes reciprocal, sometimes multiplied, and then summed across all the edges. So that here the two method methyl phenethane, it can be molecule can be shown here in the figure, and this totality we are calculated here. Each edge 1 into 3, 1 into 3, and 3 into 2, and 2 into 2, and 2 into 1. We get the sum, you get 18. This is one of the simple started with a graph invariant. Now in my study, I taken one of the thymidine. Thymidine is a sometimes known as deoxythymidine, deoxyribosylthymidine, and thymine deoxoribine. Is a pyrimidine deoxynucleoside. Here it is the DNA nucleoside T, which pairs will be A and double stranded DNA. This is the one of the important DNA nucleoside is useful in cell biology, and also synchronize the cells G1 early S phases. The chemical formula of this thymidine is C10 H14 N2 and 5. I taken this is the one of the interesting properties of thymidine. That's why I chosen this as my reference of my talk. Already I mentioned how to choose the molecular structure of any structural thing, that is thymidine molecular structure of a thymidine. Here it is V12, you get V16. There are 16 vertices, and we get the graphical representation molecular structure of thymidine is this one. Now we will move on to what are the different types of graph invariant. Generally, one of them is distance based, distance we calculated. Then another one is degree based GIs, that is graph invariants, and neighborhood based GIs, and interconnected GIs. Maybe it is degree distance or degree neighborhood and neighborhood distance, and some of them will be the interconnected GIs. These are the majorly we classify into types of GI. Now I will choose that distance-based edge partition. You can see the distance between 1 and 2. There are, if you observe here, there are 16 will be there, the total number of edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Here, similarly, here we calculated the pair, the distance from U to V, the number of edges is 17. Similarly, the distance is 2, the number of edges is 20. And similarly, 3, 21, 4 is 17, 5 is 15, and distance 6 is 11, and 7 distance is 8, and 8 distance number of edges will be the 4. And 9, the distance will be only one of them. After making the distances, now we move on to a distance-based graph invariant. First, I make a tabulation form, then we can go to first study is useful for our discussion. Wiener is one of the oldest graph invariant. That is the first graph invariant introduced by Wiener in 1947. That is the sum of the lengths of the shortest path between all pairs of vertices in a connected graph G. This is the formula defined by Wiener. It is the first graph invariant introduced. for molecular study. That is summation of degree of UV. This is a simple calculation I already mentioned. That is 1 into 17. There is 1 edge into number of edges, 2 into degree into 20, 3 into 21, and 4 into 17, and 5 into 15. The table, using the table, we calculated the Wiener index of iodine. Similarly, one more important index, that is in 1993, Milan Randic introduced the distance-based quantity. He named as hyper-Wiener index, and it is denoted by HW, and this is useful for applied only to trees and was possible to use cycle containing graph. Any graph containing cycles type, then we can utilize this graph invariant. This is the formula for distance Milan Randic index, that is HW, hyper-Wiener index, that is summation of the distance of u comma v plus d square uv divided by 2. The h already we mentioned, we already calculated d of u comma v, that is Wiener index. The part, this is hyper-Wiener index, that's why that is 426 we calculated here. That can be taken and square, and we get the sum of this. You get a hyper-Wiener index of iodine. Why I am telling these things means, if you seeing this property, we thought that it is a very simple concept. Our UG undergraduate and graduate students can also study this one very easily. Then they can extend it to the n variables. Now I will move on to a degree-based edge partition. You know that the number of edges, the degree is 1, 3. You can see here the degree of this V1 is 1, and degree of V2 is 2, and degree of V3 here 1, 2, 3 will be there, and here degree of here 3, here also 3, and here also 3, here 2, this is 1. This is using this degree based topological index, we make the degrees 1, degree, number of edges is 4, number of degree 2, 2 is 1, the combination, the edge, and 3, 2 is 9, and 3, 3 is 3. This is the edge partition of the thymidine we are chosen, and in the this is degree based topological indices. This is the first and second graph indices among the oldest and best known graph invariant defined in 1972 by Goodman. This is the M1 of G is equal to summation, that is degree square of E, G, and here another one is D, G, and multiplication. This is known as first graph index. This is known as second graph index. This two indices are many applications in mathematical point of view as well as chemical point of view. And if you see this paper, more than 10,000 citations are appear. And after seeing this degree-based topological index or graph invariant is motivated by many researchers, and also they extended and also modified these Zagreb indices. And also this is a computation majorly used in the computation of total pi electron energy of molecule within the specified approximate expressions. This is the fundamental thing to study the first and second Zagreb indices. This is the calculation of the first Zagreb indices of thymidine. That is M1 of G is equal to, we use the formula 4 times 1 square, 8 times 2 square, and that is 8 distance. 4 times 3 squares using this table. And similarly, calculation of second Zagreb indices also study with respect to 4 times 1 into 3 and 2 comma 2 the combination and 3 comma 2 combination is 9, 3 comma 3 is 3. We get the value for that thymidine calculation of second Zagreb index. Now, degree base, one more important graph invariant that is known as harmonic index. In 2017, Zangre introduced the harmonic index for the study, that is h of g is equal to summation 2 divided by u of g plus dv of g, and this is the edge partition, that is uv belongs to e of g. Exactly similar calculation you can see here, 4 into 2 divided by the combination 1 into 3 and 1 into 2 divided by 2 comma 2 combination, 3 comma 2 combination edge partition and 3 comma 3 combination. You get the value for the harmonic index of thymidine. One more index, that is forgotten graph invariant, introduced by, this is known as forgotten topological index. Sometimes we utilize, that is Frotula and Gutmann in 2015 is defined f of g is equal to g dg of u whole cube. We can use that same degree based table. We can find 4 into 1 cube, 8 into 2 cube plus 5 into 3 cube. You get a calculation of the forgotten topological index or forgotten index. Next, the one more first genuine degree based graph invariant. I already told that Milan Randic is the main person. In 1975 also he introduced, that is known as Randic index. The name after this introduction, they are told that it is a Randic index. He find for characterization of a molecular branching. Using that molecular branching, that time he introduced this first genuine degree based graph invariant, that is known as the topological descriptor that can be correlated with many chemical characteristics of molecules and has been found to be parallel to computing for majorly boiling point and Howitzer constants of a molecule. This is the definition. R of G is equal to summation 1 by root of d, 2 of G and dV of G. Here, the calculation I already mentioned how to calculate this Randic index of thymidine. Means same 4 into 1 into 1 into 3, the combination of the partition of the edge relationship, UV edge 1 into 3, 2 comma 2, 3 comma 2 and 3 comma 3. We get the simple calculation for this. In order to graph invariant, the order to take information of Estrada, this is also one of the main important scientists. He introduced the new graph invariant, the updated version of the Randic index. It is known as atom bond connectivity index. So always we referred as ABC index. The atom bond connectivity index provides a very good correlation for the stability of linear alkanes. That is also a branches of alkanes and also compute the strain energy of cycloalkanes. This is the definition of ABC index and root of du of G plus dV of G minus 2 divided by du of G into d. This ABC index having many applications and mathematicians are also studied by majorly the K.C. Das of South Korea. He is one of the top 2 scientists. He is done many work related to this graph invariant. This is the calculation part of the atom bond connectivity index of thymidine. This is ABC of G is equal to summation. This is the definition of this. You can exactly study the 1 into 3 minus 2, 2 comma 2 plus minus 2 divided by, you can number of edges. That is combination, apply, you get a ABC of G. And this is one of the important aspect. Wotsolova is introduced the 148 Adriatic indices in his paper, that is atom additive formulas for atom bond connectivity indices. That is one important paper. In that paper itself, 148 Adriatic indices are introduced. In that also tested by International Academy of Mathematical Chemistry. In that paper, one of the beautiful index, that is symmetric division degree index, attracts more attraction to the many researcher. In this, I also attracted more on this symmetric division degree index because there is a symmetric property can also be applied to the apply for the this symmetric division degree index.
Hello, Professor.
Sorry, so this is some internet connection. Okay.
It's okay.
I also attracted for this symmetric division degree index, and we worked on this with one of professor from Canada. That is, she invited me to in Manitoba University for 1 month for studying this symmetric division degree index. Both we worked on this symmetric division degree index, and we produced 2-3 papers, and also one of my students worked on this symmetric division index, and she produced she published 3-4 papers related to symmetric division degree index. And this is the calculation of the symmetric division degree index of thymidine, that is du of G whole square. This you get a 40.833. This is the simple calculation, because how to start with the any index. Now I will move on to there is a combination of degree distance. The degree distance was introduced by Dobrynin and Kochetova as a weighted version of the Wiener index. This is the higher weighted version of the Wiener index, that is denoted by dd of G, here degree as well as distance of combination of both will be there. That calculation, you already know how to calculate the degree based topological index as well as distance. And merge this, you get a calculation of finding the degree distance of dd of G. We can get W Kochetova is introduced. And now we move on to a neighborhood based degree indices, that is how many neighbors are there for the number of edges. 3,6 neighbor and 2,4 and 4,7, 6,7, 6,6. This is the some combinations of the neighbors. And the number of edges, total number of edges are we calculated using same graph. I chosen for the same graph for the purpose of study. This is neighborhood based edge partition. In 2017 and 2019, he wrote this paper. That is, one of my friend, Vasumani, proposed a new graph invariant named as Sanskruti index S of G. Of a molecular graph G can be utilized for bioactivity of a chemical compound. It is denoted by S of G, summation of S of U into S of V into S of U of G plus S of V of G minus 2, the cube, where S of U is the summation of the degree of all the neighbors of U in G. This is the calculation of the Sanskrit index of thymidine. The combination I already mentioned, 3,6, that is this table. Using this table, 3,6, number of 3 and 2,4, 1. Using that, here we can substitute 3 into 6 divided by 3 plus 6 minus 2, 6 into 2 into. We can substitute because it's a simple mathematical calculation and get a value for the calculation of Sanskrit index. Next, recently in 2020 and 21, a graph G is said to be distance balanced. That is, Moster index is introduced recently. A graph G is said to be a distance-based balanced if every edge UV, the number of vertices lying closer to U than V is equal to the number of vertices lying closer to V than U. This is the meaning. The number of vertices lying closer to U than V is equal to the number of vertices lying closer to V than U. That is the meaning of this. Doslik and Ithal proposed a new bond additive structural invariant called Moster index. Nowadays, many people are working in this. These are some of the restrictions are also there for Moster index. This is the simple calculation for, this is the molecular structure, V1, V2, V3. I have not taken the for calculation of thymidine. Here I taken for one more simple structure, that is V1, V2, V3, V4, V5, and V6. This is the calculation. You can take here first one, 1, 2, 3, 4, 5. This is 5 minus 1, and another one is 3 minus 2, and 3 minus 1, and 4 minus 2, and 3 minus 1. You get 11 for the Moser index of this graph. Now, actually, in the starting with itself, I told more than 6,000 topological index or graph invariants are there. In that, I taken few of them for the purpose of study. Many of them interested, they can enter in many graph invariants are there, they can study. This is how to start with the basic structure, degree, distance, neighborhood, and the combination. This is the fundamental thing I introduced. In the graph operation, simple graph operation must be known because after the operation are the characterization for the purpose of the study of general graph. These operations are important, or operators are also important. The line graph, everyone knows that the L of G is the graph vertex set. VL is equal to edge set. Vertex become edge become a vertex. That is known as the line graph. It is in an introduction of total graph, coloring, and line graph in 1963. Chartrand and Ithal are introduced. And subdivision graph, because some of the part we are utilized in our paper, Nancy and our team. That is S of G, subdivision of G means if you divide any graph, we can introduce any one vertex in that becomes splitted. That is known as subdivision. In our paper, the certain graph invariants of the derived graph using neighborhood things, we utilize this purpose. Next is vertex semi-total graph, that is T1 of G, or also some of them are of G. You can see this is the original graph. First, we can introduce here, wherever the edge is there, you can introduce the vertex here, here also vertex, here also vertex, here also vertex, because edge. Then you can join that. Then you get a vertex semi-total graph. Next, edge semi-total graph, sometimes we utilize as Q of G is a notion, and T2 of G, some of the others are mentioned. Here, wherever the edge is there, introduce the subdivision here and here, here and here. Then you can join that. The edge, wherever the edge is there, you can join. Then you get there is a relationship. Then you get a edge semi-total graph. Next, the totality of the graph means both semi-total, edge and vertex. Then you get a totality of the graph, both edge as well as vertex. Now we move on to one more, that is gem graph. Gem graph is defined as the graph defined as edge E of G, and in which two vertices are adjacent if and only if they are not adjacent in the gem graph. Here, this edge becomes a vertex. Similarly, here the combination, there is a relation, you can write a edge. Now, paralleline graph. The paralleline graphs are more important in chemistry. Here, the paralleline graphs are interdisciplinary in chemistry and graph theory. I will give you a simple example for this. This is the hydrocarbon of C6H6. This is the graph of C6H6, and this one is known as paralleline graph of C6H6. These two are the given graph. Insert two vertices in each edges of XY, and also those two vertices can be denoted by X comma Y or Y comma X. And tensor product. Nowadays, it is more popular because the combination of two graphs can be done by tensor product. Here, we given simple example of taking path of P2 and cycle graph of C5. Then the tensor product of these two, here we can make here A1, A2, A3, A4 and A5 as the vertex. Similarly, B1, B2, B3, B4 and B5, the combination, you can relationship, you get a tensor product of P2. This simple example I mentioned. Now, the tensor product introduced by Alfred North, Whitehead and Breton in 1912, because we are utilized in the discrete mathematics, that is Kronecker product as adjacent matrices of a graph. The cross symbol shows visually for two edges resulting from the tensor product of two edges. Sometimes it is known as direct product, cardinal product, relational product, and weak direct product or conjunction. Using these, we can connect the four related S of G, that is subdivision, and semi-total, semi and total graph. This is the four operations if you chosen. Here C3, S of G, S of C3, then this is R of C3, and this is Q of C3, and T of G, T of C3, that is known as graph. This is a graph, and we can make all the four. And F-sum graph, nowadays the forgotten topological index, using that forgotten topological index, F-sum graphs are make it into a picture. This is the black version. You can see this the graph operation apply. F-sum graph, that is G and H two graphs, and apply to the four operation S, R, Q, T, means subdivision and semi-total, and these can be make it in this definition. We get AIJs are black vertices, BIJ are white vertices, this one. Now, after that, P2C4, the connected to the example of new operation. I already mentioned this P2C4, P2C4 of subdivision, semi, first operation, second, and total graph. Now, this is the same. First, I'm introduced some of the graph invariants, now operations. Now I will move on to our new graph invariant introduced in the name of VL index. That is my, she introduced in my name, that is in 2020, that is introduced by my one of student Deepika T, motivated from the first and second Zagreb indices. That is, you can see here DE, DU plus DV minus 2, and DF is the combination of DU into DV minus 2. There are degree vertices of U1 and B. This paper, she worked, this is the definition, but she applied to a bounds for the tensor product of SM graph for the VL index. That is published in TWN's Journal of Mathematics, Applied Mathematics and Engineering. This is the VL index can be, this is the definition I already mentioned. Here she taken simple graph for our purpose. Here you can see 1 into 1 plus 3. Here you can see the degree based topological index here. This is degree is 1. Here degree is 3. Here 1, 2, 3. And 1 by 2 times 1 plus 3 into plus 1 into 3. Similarly, the second combination, this 8, you get a 18 point of. This is an impact of index in the area of research. The chemical reaction changes entropy. Entropy play an important role in determining in which the direction a chemical reaction spontaneous process. A role of enthalpy of vaporization is a transform the quantity of the substance from liquid to a gas at a given pressure. That's why, furthermore, physical properties of octane, PCB, that is polychlorinated bifluorine, has also a vital role in a chemical application. I already mentioned, motivated from this Goodman's result, to introduce that one. There are many papers that appeared in the Zagreb indices. Majorly, my one first student, he worked on the good works on Zagreb indices done by Ranjini and his team. Their extended version become the most interesting part of the research because it's applicable in chemical sciences. You can see the following table. You can see here the correlation relationship, that is entropy value, enthalpy vaporization, standard enthalpy vaporization, acidic factor, and physical properties. Here, this is the, I already mentioned, what is the main aim means. The treadmill, the calories burned can be given example for this. It is usually varies from the correlation coefficient lies between -1 to 1. And if it is closer to 1, then the variable, we say that it is highly linearly proportional. And if it is closest to -1, then we say that highly linearly inversely proportional. If it is 0, then we say that it is no relation. This is the observation we mentioned for the octane isomer with respect to a VL index. The things you can see here, correlation coefficient, and also some of the graph you can see here, the VL index with enthalpy and VL index with enthalpy vaporization. And this is the VL index with standard enthalpy vaporization with respect to R square, and also VL index, it is correlated with the acidic factor. And VL correlated with the physical properties of VL, that is relative retention time, RRT. This is the already in the 2-3 years back, she studied by VL index. Now recently, seeing the status of a vertex in 1959, F. Harare introduced this status or transmission of a vertex U belongs to V of G, denoted by the sigma g of u is that defined as the sum of the distances between u and all vertices of a graph G. Here, I will mention how to calculate the status or transmission of a vertex. If you take the first one, the status of V1 is equal to, you can see here it is V1 to V2 it goes, this transmission goes to here, and this is also 2. Here 1, V1 to V2, 1, and V1 to V3 is 2, and V1 to V4 is also 2. Then you get the status of vertex of V1 is 5. Similarly, you can calculate V2, V3, V4. This is the status. After observing this status of a vertex of a graph, and Dobrenev and Kochetova introduced the first status connectivity introduced. Then motivated from these results, our scholar, that is Suvarna, introduced in the observing the VL index and status index as well as the status connectivity index. All three observations, she introduced the VL status index as well as PUI index in this way. Only if you introduce the index, it is not that much useful. Then there are where it is applicable. That is also one of the important aspects. That's why she checked. First, I will show how to calculate the VL status index. Same graph, you already calculated the value. Simply substituting this, you get a VL status as well as VL co-index, status co-index. And now the main important theme is the correlation of VL status index. That is QSPR studies from very beginning its journey sees the attention of the mathematicians I already mentioned. Finding the properties of a compounds without any experimentation that is actually time consuming, as well as the money will be very less. Here we see the VL of S, that is status index, as a good correlation with three physical properties: surface tension, complexity, and heavy atomic form. These are the three, that is values are 0.85, 0.87, and 0.85 respectively. This is the correlation of VL status index and some properties of butane derivatives. And using the data of the table 1, the scatter plot between the surface tension, heavy atomic count, and with respect to VLS of butane derivative are shown in this figure. This is the correlation of VL status index with physical properties of butane derivative. Then, in the mathematical point of view, there is a bounds. If you find a bounds, then it becomes useful. This is the let G be a connected graph with n vertices, and diameter of G is equal to D is the notion E here, and this is the inequality, that is bounds is founded by any connected graph. This is, we are introduced for the simple graph for the checking purpose. Now it can be extended to the connected graph with n vertices. And also there are some corollaries related to that also established using the concept of VL status index with respect to diameter and also the minimum and maximum degree. These are some of the results related to that, and with respect to particularly connected regular graph and connected graph, and also the general graphs. Because if you take any complete graph of Kn of n vertices and m edges, this is the results for m comma n is the, the graph structure, m vertices, n vertices and m edges. This is the results for the complete graph of Kn. Similarly, the bipartite graph of VL status index. And also path, general path, this is the relationship. and cycle. If it is n is even, if n is odd, this relationship will be holds. Similarly, wheel graph and friendship graph relations. And also PL status co-index relation also studied similar way and characterized the equality of these bonds. And VL co-index she studied with respect to complete and complete bipartite graphs. Here I am not shown the proof structure, only I mentioned some of the highlighting the results related to VL status index. That is wheel, cycle, and windmill graph. After that, one more, after working on many results related to status index, she also attracted by reciprocal status vertex. H.S. Ramani and his co-authors are introduced the reciprocal status index, the definition. Here we introduce using this reciprocal status definition. Here you can see that is same D of V1 to V2 and D of V1 to V3, that is reciprocal structure applied, and you get a reciprocal status. First, we can find a reciprocal status. Using that, you can introduce similarly in the reciprocal status index and as well as co-index. That's the calculation. You already know how to calculate the reciprocal status index and also co-index. And the main important again, that is also the physical properties of surface tension, complexity, and heavy atomic counts, exactly similar, more accurate than the status index, VL status index. This is more powerful than the VL reciprocal status index is the in terms of VL status index. This is the same reciprocal status and properties of butane derivatives, and this is the VL status co-index of butane derivatives physical properties of the correlation relationship. And exactly similar way, after seeing the previous results and this one, you can observe here how the bonds are more characterized in terms of VL reciprocal status index. And with respect to minimum, same results can be more accurate, characterized in the VL reciprocal status index. And also, she calculated the complete graph of VL's reciprocal status index, complete bipartite index, path of PN, cycle, wheel, and windmill graph results. Co-index also she studied. And one more important paper, that's VL temperature index of Archimedean lattice. There are three in this talk. I mentioned the two VL index, then how the status and reciprocal status, and one more is the temperature index. Here, the Simon introduced the temperature of a vertex. How to find the temperature of a vertex? Here, du is the degree of the vertex u with the connected graph G, and n is the total number of vertices graph G. In this simple example, you can observe here there are 4 vertices are there. Then here degree of V1 is 1 and 4, therefore 1 by 4 minus 1, you get 1 by. Similarly, you can calculate the other vertices. You get each vertex temperature. This concept can be extended to VL index, VL temperature index. Then after seeing this temperature, the Archimedean lattice is the one of the important structure, that is infinite transitive planar graph can be drawn in a plane such that all faces are regular polygon. A regular polygon with m edges is a polygon where the edges have the same length. In this, she taken The Archimedean lattice, some example, that is LF 4,8 square and 4 power 4. This is LF 4,8 square Archimedean lattice. It is LF 4 square Archimedean lattice. This is LF 6 cube. Using these lattices, she calculated first she done the subdivision graph of that is L 4,8 square. You can see sometimes you can see in the floors there are different distinct diagrams are seen. This is the beautiful structure of a Archimedean lattice. In this structure, she calculated the line graph of the subdivision. Means operation can be applied to the Archimedean lattice. Then she calculated the structure in the tile model, how the temperature can be checked by using this by line graph and of the subdivision graph of the Archimedean lattice. Similarly, she studied the same thing in L44 and 4 power 4, 6 cube, and that is the chemical applicability of also studied by VL temperature index. That is complexity, density except surface tension, heavy atomic count, and index of refraction. These are the three properties she studied by surface complexity, HAC, and density index of retraction. These are the chemical applicability of the reaction with respect to VL temperature index. And that paper, that is VL status index, is published in one of the journal, that is Indian Mathematical Society in 2021. And after that, some of the results related to VL temperature index in general with respect to Wiener index and other indices also, the correlated with M1 and M2G and VLS and co-indices, the interrelationship between the other Zagreb indices also mentioned, and find the results related to status index and co-indices. These are the some automorphism is applied to the VL status index. That is also transmission. You know that this is the transmission regular but not degree regular graph with smaller order. And some results related to connected K transmission regular graph and also automorphism graph with respect to vertex G. Then this is the results related to VL status and VL status co-index. And hypercube also we can study. You get the results for, and Nasser graph of VL status and co-index also she studied. This is the nanostructure, HRL polyx, nanotorus perimeter and length. This is also applied to the VL status and co-indices, reciprocal and other indices. Now, because of time permission, I will mention there is a relationship between the NM polynomial. We can make it this index or graph invariant to a polynomial structure. This is one of the simple NM polynomial effective for recovering the neighborhood degrees sum based graph invariant that predict different physical, chemical, as well as biological properties of a material under investigation. Because the neighborhood M polynomial of synthetic polymers can be obtained, and synthetic polymers are derived from petroleum oil and made by scientists, engineers. These are some of the important examples related for this study. Examples of synthetic polymers include nylon, polyethylene, polyester, Teflon, and epoxy. Natural polymers occur in nature, can be extracted, you know that in silk, wool, and DNA, cellulose, proteins. The neighborhood M polynomial is effective for recovering neighborhood degree sum based graph invariant. They predict I already mentioned this, this is the NM polynomial derivative of NMR, and these are the derivative and Sx. Then you get a results. This is the hydrogen depicted molecular graph VRMN, and this is the Wagner rubber network NM polynomial can be calculated. These are the different examples related to. These are the three important concepts I want to study. First, how the graph invariants are there. Many graph invariants are there. In that graph invariant, I chosen some of the graph invariant. In that graph invariant, some of the motivational work the recently introduced by one of the graph invariant, and many alternative interrelated graph invariants are also structured. Then, and how the mathematical calculation can be done by that topological index or graph invariant. And now finally, I will tell you how we can make a method for developing this index. First is direct structural interpretation, good correlation with at least one property, good discrimination of isomer, locally defined, generalizable to higher analogous, linearly independent, not trivially related to other indices. Means you must check other indices, it is already introduced or not. And efficiency of the construction based on the familiar structural concept, and gradual change with gradual change in the structure. And QSPR analysis, mathematical property, characterization of extremal graphs, characterization of graph with equal degree based topological indices, graph operation. These are the minimum concept for any graph invariant. Now, in the last part, that is software utilization. Because always we cannot make manual calculation. Simple graphs are simple things we can calculate manually, but generalization and general structure, we need software. It's softwares for higher dimension, plotting of a graph or Mathematica, MATLAB, SPS, and Python. These are the simple things. Statistical SPSS will be useful for correlation regression, linear regression model, and standard error can check. In the mathematical MathChem, Python package or Dragon software for calculating graph invariants and properties for graph topology. Sage Math is one of the open software help us to construct the graph networks and calculate graph invariant. And also we can use using that Sage Math, we can visualize the graphs. These are some of the examples and some of the list of modification methods of graph classes in the commands, and base properties with respect to class method and description, and coding for the how to calculate some of the direct calculation purpose. If you import MathChem with mathchem.mol, you get a result for directly we can calculate the first and second diagram, and basic standard graphs they already make in Sage Math. These are some of the class methods with respect to graph invariants or topological index are already inserted. Newly index can be merge and do the algorithmic part, and you can use Python package and introduce. Python package for calculating graph invariants provided example of joint use of other well-known open softwares, products such as Sage Math. Because it cannot solve MathChem directly, we can use for computation of research in mathematical chemistry. These are the recent publications of our team. That is one of the paper I already mentioned in the thing, and corona product graph of SK indices, and discrete Adriatic indices of probabilistic neural networks in European Journal of Pure and Applied Mathematics, and VL reciprocal status and co-index graph in proceedings. Recently it is published. And Southeast K. Banahati of certain graph invariants, and also graph invariants of bounds of graph invariants can also recently published, and investigation of splice graph of exploiting certain graph invariant, it is published in Proceedings of Janjian Mathematical Society. Recently, one of the semi-total graph of neighborhood edge corona graph of two graphs with help of Professor Defik and our team done this paper. Recently, it is accepted in the European Journal of Pure and Applied Mathematics. Adriatic indices and Sanskrit index of envisage carbon nanocube. These are the recent publications, because we published more than 100 papers related to topological indices. Recent work can be seen in this paper. And any graph theorist must read these important books, that is bricks. And if you need a matrix calculation purpose, we can use Ravindra B. Bhatt, and Introduction of Chemical Graph Theory. This is useful. And covering walks in graph. This is also useful for studying the trees and other aspects. And Handbook of Graph Theory. This is some of the useful books for anyone is studying the topological index with respect to graph theory. Thank you. Thank you very much for giving opportunity to share my thoughts in this conference, because I'm not given any new results in this. Whatever our younger researchers worked on this area, topological indices as well as graph invariant, that I can highlight the points. I'm basically interested to motivate the graduate student, those who are entered in the field of graduation, that can be motivated and work more on this area. Thank you. Thank you very much.
Thank you very much, Professor Lokesha, for the very inspiring talk about the investigation of graph invariant and its relevance. And now we go on to the discussion time. For audience who has a question, please welcome. You can write your question in the chat box, or you can use the raise hand feature in the Zoom meeting if you want to ask directly to the Professor Lokesha.
Also, some of you are not ready to, you can send a mail to me. Definitely, I will answer. If your students are not directly answered, anything related to our area, definitely I will give you insights to the this graph invariants.
Okay, well, ladies and gentlemen, is there any question? I think your presentation is clear enough, Professor Lokesha, and it was so interesting. And maybe next time we can have a joint research together.
Thank you. Thank you very much, ma'am. Thank you for giving opportunity for sharing my thoughts in this 6th International Conference. And also I congratulate whole team for the organizing both hybrid mode, both online as well as offline mode. Thank you. Thank you very much for the special thanks to my friend Dafik. And also I'm very happy that Venkachalam is also there. He is also enjoying with some of the good research aspects it can be learned. And because morning he told about the how the research lab, your research lab is excellent. I'm eager to waiting for seeing your lab and other things, Professor Dapik. Thank you. Thank you very much.
You're welcome, Lokesa.
Thank you.
Nice talk. Hopefully you can visit my university. Yeah,
Thank
just,
you.
me, I have the beauty of rector for academic affairs. He said that you are welcome to come down to Indonesia next year.
Thank you. Thank you. Bye.
Okay, thank you very much, Professor Lokesa. Before we go on to the next presenter, let me read a little concluding remark about the Professor Lokesa talk. The title is about the investigation of graph invariant and its relevance. The topological index is already set for graph invariant in molecular graph theory. In the mathematical and chemical literature, plenty of graph invariant have been introduced extensively and studied. And there are various applications to help us construct a graph network and calculate graph invariant, such as MATLAB, Maple SPSS, and the open source one is ICCGANT. Okay, thank you very much for Professor Lokesa. Let's give a round of applause for Professor Lokesa. Okay, well, ladies and gentlemen, we go on to the second speaker in the second day of ICCGANT 2022. The second presenter, the second talk will be delivered by Professor Slamin M.Com SC PhD from University of Jember. Before we go to the talk, let me read the short CV of Professor Slamin M.Com SC PhD. Professor Slamin is a professor in the study program of Informatics, University of Jember, Indonesia, and completed his master's degree and PhD degree from the University of Newcastle, Australia. Now he is a vice rector for academic affairs in the University of Jember. Professor Slamin's research interest is in graph labeling, optimal network, dominating set, metric dimension, graph coloring, and information technology. Okay, well, ladies and gentlemen, please welcome our invited second speaker, Professor Slamin M.Com SC PhD.
Oke, langsung ngomong ya. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, yeah. And I'm now speaking as scientist, as graph theorist, not as rector anymore. Yeah. Okay. First of all, thanks Prof. David for inviting me as one of invited speaker in wonderful conference, yeah, ICCGANT. I think this is the sixth ICCGANT in 2022. Now, my talk is about graph theory in various applications. But in this talk, because another talk, I think at the end of this month, yeah, I will talk another application of graph theory. So in this talk, in this ICCGANT, I will choose the application of graph labeling and coloring. Yeah. Okay, so there are at least six, because this is six ICCGANT, so I choose 6 applications of graph theory in this talk. The first one is magic polygon. The second one is scaling system. The third one is network addressing, Olympic emblem, chemical storage, and the last one is in the game, yeah, Sudoku puzzle. Okay, first it's about magic graph labeling. I think everyone almost everyone knows about magic labeling, because this topic is, I think, the most favorite topic in graph theory, because it is recreative topic, and this is actually introduced by Kochik and Rosa. Well, there are some other type of graph labeling, which is already introduced by other researchers. But as far as I know, the first published paper about graph labeling was given by Kochik and Rosa. They define that magic labeling of graphs is one-to-one map from vertex V and age E of the graph to integer 1 to up to the number of vertices and edges, such that the weights of every edge of the graph is constant. And each weight is the sum of the label of edge and is each to n vertices. Probably I can. Sorry, I think I have maps here. Oh, sorry. I hope the slide is still with us. Okay, so what we have here is so edge width is usually we call it no, sorry, why I can't use it. Okay, my hand is better than the pencil. Okay, this graph labeling also known as an edge magic total labeling, which is because there are various type of magic labeling. It depends on the weight, where the weight is counted. So Wallis, Mirka, Miller, Edith and myself is redefine the name, only the term, only the terminology. So we call it this type of labeling by edge magic total labeling. Okay. This is the example of magic graph labeling, as we know that the weight, the weights of the air is all equal to 29. I think it is clear. Next, there is an interesting homework given by the teacher in actually in Union High School in 7th grade. The question is, this is in the books of, the compulsory book. What is the compulsory book? The handbook for 7th grade student in Union High School. The question is, they have to place the integers 1, 2, 3 up to 6 into 6 empty circle in each corner and side of the triangle. We call it trigon because we can expand into n-gon, such that the sum number of every side is constant. So we can see that here they have to be constant. They have to be the same. So when we place the numbers or the integer, we have to get the same sum on the each side. And this one is actually appeared in Instagram. In Instagram, to be exact, it is in Impulse akun, Instagram into actually 2 years ago, and exactly the same as a question in the Union High School group. We need to place like integer from 1 to 6 into the small circle, such that the sum for all sides of the triangle should be 9. This is not mine. This is someone else. Okay. Now, of course, we know the answer. It is very, very easy. But if we expand to n-gon, especially the even M, it is not as easy as we imagine. I know that in that time, no one in my home can have my son to solve the problem at the time, unless for this triangle, for the other gods, for other n gods, nobody can solve that, especially for n is even, And then we just realized that actually we can use this labeling, the arithmetic total labeling. So basically, we just represent the circle by the vertex, I mean the circle of the corner by the vertex, and the circle in the side, in the middle of the side by the edge. So we just label, the vertices at the edge of the triangle, using arithmetic total labeling, and that's it. So we can use this labeling. We just convert the labeling, for the triangle into the circle, So we can have here 1, and we can have here 6, 5, 6, and so on. So what we have here, we can have magic constant k equal to 9, and of course, because we already solved, the arithmetic total labeling for any n cycle. So this magic polygon is totally solved, using arithmetic total labeling. But the question now, we can use expand, we can expand the magic polygon such that the number of circles in the side not necessarily 1. It can be m, probably, It can be the same m, or it can be not the same number of circles, such that, for example, maybe the number in one side is m1, the number of circles in the other side is m2, and so on. So you can, but this is not solved yet. But for the same m, this is already solved. Okay. Now we can continue to arithmetic total labeling. The previous one is arithmetic total labeling, but now we talk about arithmetic total labeling. For this one, it's actually the same. You can label the vertices of edges by 1 up to the number of vertices and edges. But the weight is counted in the vertex. Such that every vertex has the same weight. Okay, this is the example. You can see that the magic constant for, sorry, this is not arithmetic total labeling, but vertex magic total labeling is k equal to 16. 16. So you can have here this one, 16, and this one is also 16. This one is also 16, and this one is also 16. Okay. Now, what is the application for this one? You can see that actually this is also what's called question in mathematics Olympiad for high school. In Australia, especially the question is the Olympic emblem. You know Olympic emblem, right? This is the Olympic emblem. We just need to place $1, $2, up to $9, because you can see that in this emblem, you can see that there are 6 regions for this. Sorry, 9 regions for this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So we need to place the amounts of $1 up to $9 into every region, such that in one ring, in each ring, we can get the same number or the same amounts of money, of dollars. So you can see that one. So what we have to do here, we represent this Olympic emblem into graph. And this is the graph. Okay, you can see here. So we represent the range by vertex and the intersection between rings, between two rings by the edge. So after that, we just need to label this vertices and edges of the graph, yeah, using vertex magic total labeling. So we can have here that the weights of the vertex is the same number, yeah, which is equal to 11. So you can see here that the every rings in Olympic emblem, yeah, contains the same number of dollars, the same number of money, the same amount of money, yeah, which is $11. Okay, and of course we can extend the number of rings as many as you like, yeah, to obtain the general solution. Yeah, and we already solved this. And in fact, this one is actually part. Yeah, and for part, we can have that the technique total labeling on part. Yeah. Okay. Next is this one. So another application for this labeling is, of course, assignment of network address. Yeah, we can see that the problem in the network addressing is we need to label, yeah, label the client, yeah, the terminal, yeah, and also the link, yeah, such that in every link and every terminal, we use the different label, yeah, the different label, yeah. But the question is, we need to like use the same code, yeah, the same code. I mean, something like key or password, yeah, to make sure that every message come to the right terminal, yeah, come to use. I mean, you use the right channel such that the message come to the right client or terminal. What we have here is actually we use edge magic total labeling. Yeah. For example, if we have this device, yeah, in some network, yeah, you can represent this device into graph, yeah, and you can see the graph is like actually this is binary tree, and we can use the edge magic total labeling of the tree, yeah, such that every edge have the same weights. So what we have to do in the network addressing is, when we know that the magic constant k is equal to 41, then if we send a message from this client, this terminal, yeah, and we want to use, I mean, we want to send to this terminal, so we have to use this channel, this link, yeah, 25. So we make sure that the message is come to the right client, to the right terminal, right? Okay. The next one, well, there are many research on graph labeling, yeah, lots, yeah. And if you want to know the progress or the status, you can see this, the last reference, yeah, a dynamic survey of graph labeling, which is initiated by Galian, and I think someone take over that after Professor Galian passed away. Yeah, but I think this survey is still updated. Yeah, but as far as I know, the last one is in 2020. Yeah, I hope somebody can find the new one, the newest one. Okay, now coloring. Yeah, graph coloring is also very famous topic and very popular topic, yeah, in graph theory. Yeah, I think you know that the history of graph labeling is actually start from a letter, yeah, from letter that's penned by the Morgan to Hamilton. I think you're familiar with that two name, yeah. The Morgan, the Morgan law is a set, yeah, and also Hamilton. Hamilton is very famous in mathematics, especially in graph theory. Hamiltonian cycle, right? So, and the first proof is given by Kempe in, nobody here was born in this year, yeah, and he would in 1890 found a mistake, but he used 5 colors, so he haven't solved the problem, yeah, this four color theorem problem, yeah, and then Apple and Hyken proved in 1976 using computer, but of course mathematicians didn't happy because they want to use mathematical proof, yeah. Then Robinson, Sander, Seymour, and Thomas improved the result, yeah, in 1997. But of course, they still use computer to solve the problem. Of course, mathematicians still didn't happy, yeah, until Gondier gave a formal proof. Formal proof means mathematical proof, yeah, and the paper was published in 2008. Here you can see the duration, the length to solve this 4-color problem. It's almost like 2 centuries. Yeah, this is not easy problem actually. Okay, what we have here, of course, this is an example. Yeah, the easiest application for graph coloring is when we color map. Yeah, map. Yeah, you can see here, when you see that the color, either the map or the vertices of graph, you can see it just needs 4 colors at most. Yeah, it must depend on how complicated is the map, especially when you see the map in Europe. Probably, yeah, this like there are many countries there, but we guarantee that we only need at most 4 colors to color the map. Yeah. What's next? For example, this one is the example of Google Chrome. Google Chrome, yeah, because everybody use for browsing something in the internet. So you can see when we ignore the white color in the middle of the logo, yeah, you can see that this actually this logo is, if we represent by graph, this is complete graph. Complete graph. So because it is complete graph, we need like 4 colors. Yeah, there are 4 vertices in there, so we need 4 color here. But what happens if we include the white color here? Yeah, of course this is different. Yeah, you can see that this is like another vertices, and vertices. Yeah, but of course this is still 4 colors. Yeah, because this graph have a subgraph which is isomorphic to this graph. Yeah. Okay. What's next? Perfect coloring. Yeah, I think everybody knows about perfect coloring. I want to skip this definition. Yeah, basically we just color the vertices. Yeah, such that if they are adjacent, they don't use the same color. So that's the definition. The problem is we want to minimize the number of color used to color the vertices. Yeah, and the number is called chromatic numbers, the minimum numbers. Yeah. Okay. This is another version of definition. Yeah, instead of using a neighborhood, what's called, they use like proper coloring. Yeah. But of course, the definition of chromatic number are the same. Yeah. This is the example for the coloring, perfect coloring. You can see that the first one is actually free coloring. but it is not proper. Why it is not proper? Because you can see that there are two vertices which are adjacent, but they are used the same numbers. Yeah. And the second one is actually proper, but it is not optimal because they use 4 colors. Yeah. And the last one, it is proper and it is optimal. Yeah, we cannot color the last graph by 1 color. Yeah, we have to color the vertices of the last graph by at least 2 colors. So that's why the chromatic number of this graph is equal to 2. Yeah, for this one. Okay. Okay. What the application of the perfect coloring? Of course, usually we use this. This is very popular. We use this for scheduling system. Yeah, when we use, for example, we want to arrange the schedule or meeting. Yeah. For example, we have A, B, C up to E. Yeah, and these 5 members belong to 5 committees. So you can see that there are like subcommittee there. Yeah, it's called the AB, AC, BAD, and so on. Yeah, in this case, probably if you teach some subject in the class, we usually teach with other person. Yeah, we call it team teaching. Yeah. So in this case, if the rule is if there is someone there is subject have someone in common. Yeah. To teach this subject, then this subject has to be adjacent. Yeah, they have to be adjacent. Okay, and we just need the color to color the vertices such that if they are adjacent, we have different color. So, what is the fewest number of hours needed for all the committee to live? Yeah, and this is the representation of the graph. Yeah, you can see this. This is actually how they relate each other. I mean the subcommittee. Yeah, and then after we color the graph, the vertices of the graph, then you can see that actually if they are using the same color, so they can have the same type of committee. Yeah, for example, this one. Yeah. And this one. So that's why after we arrange into a table, we can have this schedule. Yeah, I think this is easy. Yeah. Okay, what's next? The next one is edge coloring. Instead of we color the vertices, now we color the edge, and the division is worked similarly. Yeah, so if the edges are adjacent, then they have to use a different colors. Yeah. Okay. This is the example. Yeah, you can see that this one is not proper. Why? Because we have this one. The red edges have some perfect in common. Yeah. They are adjacent, so they are not allowed to use the same color. Okay. This one is proper, but they use 4 color, and this one is proper, but well, they use 3 color. Yeah, and this 3 color is minimum. Why? Because the degree of every vertices, or I mean the smallest degree of vertices is 3, and it is impossible to have color less than 3. Yeah. Okay. Next, well, you can see this one. Usually, when you install flight radar application in your mobile phone, you can see how crowded as the plane is in the sky. Right? Especially now in Bali, you know, there are many planes in Bali, so they have to park in other airports in Banyuwangi or in Lombok, yeah, because there are many. Yeah, you know, you can imagine that there are so crowded in there. So when we arrange, for example, if there are 3 runways in that airport, so we have to arrange 3 planes to land in the same time. Yeah, to be landed in the same time. So we can use, and this is for, I mean, in terms of graph theory, actually it is very simple. Yeah, it is very simple. You just need to use like complete bipartite graph to get that. Yeah, so if the edges are the same, then the plane can also land in the same time. Yeah, for example, this plane, yeah, this one, yeah, for example, this plane one, sorry, this is run base, yeah, runway base, okay, F2 to F3, and this one plane one, plane 2, and plane 3. So you can see that at the same time, plane 1 can land in runway, yeah, 1 and so on. Okay, so it's guaranteed that they are not crash. Yeah. Okay. The next one is for the chemical storage. Yeah. The problem in the chemical storage is we store and different chemicals. Yeah. The interaction between some pairs is explosive. Yeah. For example, you can see that there are I don't know, chemicals sometimes it's very dangerous. Yeah. So if it is not well, not matched, yeah, and they are mixed, it can be exploded, yeah. So the problem is, what is the smallest required number of compartments? Yeah, the storage, yeah. In the I mean, the number of room in the storage such that they are not mixed each other if it cause explosion, yeah. So this is actually again we can use the coloring. Yeah, what we have here is we just I mean the crucial thing in graph is when we choose which one is represented by the edge and which one is represented by vertex. And what is the rule? Yeah, the rule like we want to connect each vertices each other. Yeah, you know that's I mean it's arranged by the rule. Yeah, if it is if you know the rule, then it is easier. So for example, if in this case vertex correspond to the chemical, yeah, and then the edge is the interaction of the chemical if it is explosive. So that's why they have to use different numbers. Yeah, then the independent set of vertices implies the compartment. Yeah, so if it is independent, then we can store the chemicals in the same compartment. Yeah, and you know, the smallest number of compartment is actually the chromatic number of the graph coloring. Yeah, I think it is easy. Okay, the last one is Sudoku. I think everyone here knows Sudoku. Yeah, Sudoku is like puzzle. Yeah, this is good to killing our time. In fact, we don't have time yet to play this puzzle. Yeah, normally this puzzle contains 9 times 9 grids or cell with digits, so that it's column. Yeah, it's column, and also each row, and also in subgrid. Yeah, in subgrid that's usually used. Yeah, the rule. Compose the grid contain all the digits from 1 to 9. Yeah, and then the question is how to reduce them Sudoku puzzle by vertex algebra graph. Yeah. Okay. Now we can like solve this Sudoku puzzle using graph coloring. You know that this Sudoku can be thought as graph contain 81 vertices because it is 9 times 9. And one vertex for each cell and 2 vertices are connected by an edge if they cannot be assigned the same value. Yeah. And all cells in the same row, column and block will have edge between their corresponding vertices. And the optimal solution in this case, of course, we have only 9 colors. It's depend on the number of column and number of rows. Yeah. So to get some good illustration, I think I only give like 4 times 4, yeah, not 9 times 9, because if it is 9 times 9, the graph will be crowded. Yeah, there are many edges in there. Yeah, and also there are 81 vertex in the graph. You can see that in this the square is actually the Sudoku, and you can see that the return of Sudoku is given by this the graph. Yeah, you just need the label. Color the vertices of the graph such that if they are connected or if there are adjacent, then we don't have to use the same color. So we have here that we only need 4 colors. Yeah, so you just need that using this vertex coloring, we can obtain our effect of the Sudoku puzzle. Yeah. Okay. I think that's all for my talk. This is the result on graph coloring. Actually, there are a number of papers published. Yeah, the new one. Yeah. So there are many problems still open. Yeah, in graph coloring, and we can like expand graph coloring using labeling. Yeah, or on the other route. Yeah, so you can use like graph labeling using graph coloring. Yeah, it's depend on the graph structure. Okay, that's all. Thank you very much. Yeah, if there is any question, yeah, we can discuss it.
Okay, thank you very much for Professor Swami for the talk about the graph theory and its various application. For audience who are joining the Zoom meeting and also in this room who want to ask question, please welcome.
Don't force them to have questions. That's all. Okay.
Okay, I think there is no question, Prof, because your presentation is very clear enough. Maybe Prof. Samin, please give a little concluding remarks about your talk.
What I have to say. All right. Okay. Thanks again for inviting me as invited speaker. At least I'm thinking about graph theory here. Yeah. Usually I just think about administration staff, thinking about what's called independent learning. And also think about a student, yeah, because I'm like organized. Manage about academic affair and also a student affair. Yeah.
How many students in general right now?
41,000 students.
41,000.
They have big size.
2,000 maybe the staff. Actually,
we have like 1,200 lecture. 200 to be exact, 233. And then I can memorize very well because I present like almost every week. Yeah. Yeah. And we have like staff, supporting staff, like 1,400, which is more than the lecturer. This is not good actually. Yeah, usually the lecturer is more than supporting staff. Yeah, but yeah, that's us. Yeah. So we need more lecturer actually.
That yesterday asked me about the possibility
to study here from abroad and having a scholarship? Is it possible? I think so. Yeah, I think so. Especially when we have like sponsorship. Yeah, but we can have like student exchange or student. We actually now focus on the what's called double degree.
I think we will start with the signing MOU between rector to rector.
Yeah, of course.
Then
Yeah, happy to do that.
you can send double degree program.
Yeah. So we just to develop the paperwork or the document and then we can sign.
But could work in combinatorics.
Yeah. And in fact, we have like PhD degree, or in mathematics degree. Yeah, I think we can do by research. Yeah, the method. Yeah, we can do by research, not necessarily take a seat in class to get some lecture. Yeah.
I propose doctoral program as well.
Yeah, of course.
Yeah.
There are really wanted in postdoctoral.
Yeah, I think I think especially when we have like research grant, so it's good to have like postdoc.
There is, we need to talk a little bit. Because tomorrow we will visit Professor Naka.
Oh, that's good. Yeah.
Professor Naka also working on
Grant theory. Yeah, this is our example. Yeah.
and we will drag you to Denpasar.
Yeah. So you will join G20.
You will give your Prime Minister. That's right.
Okay, thank you very much for submitting this post for. Okay, well, ladies and gentlemen, before we continue to our next presenter, let we have a break for about 5 minutes. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wa syukurillah wa la haula wa la quwata illa billah, amma ba'du. Good morning, ladies and gentlemen. Honorable Rector of the University of Jember, Honorable Vice Rector,
let us express our gratitude to the God Almighty. Due to His blessing, we could join and share our experience in this conference.
Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdash syakirin, hamdan na'imin. Hamdan yuafi ni'amahu yukafi mazida. Ya Rabbana lakal hamdu kama yanbaghi bijalalika wa adhimi sultanik.
Would not go in a proceedings. This talk will not go in the journal this talk is private.
Basically, people are making some matrices from given graph, and after making matrices, basically we find out the eigenvalues.
And then at the end, I will give you some open problems regarding this topic.
But the graceful labeling is not unique, so you can swap. You put the largest number or the largest label in the center, so this is can be 4 and 0 is here.
Can you regularity with some friends for the
A lot of you that will be interested to also do research in this new variation. So this.
Honorable Rector, University of Jember, Honorable Dean of MKIP, University of Jember, Honorable Chairman of ICCGANT Research Group, University of Jember.
Honorable, my friend and my brothers who are being invited speaker today, Professor.
Nobody's going to read it. But then I want you to see that actually how an important piece of results or ideas, how it's translated into a solution for an application.
This is really great. I'm very happy to be here to see the development, interest, and also activities in combinatorial mathematics. So I'm very, very happy.
those vertices, and then if the polygon is entirely on one side of that hyperplane.
Yeah. So the label of V1 must be different with 1. So there has to be 2.
Years ago, and now this year is the 4th international conference of.
It is my great pleasure actually and honor to welcome you at the present conference, which is held by ICCGANT University of Jember.
Okay, I think I am live.
Okay, you are the co-host now. And you can share your screen. You can using the share screen feature in the Zoom.
Terima kasih and selamat pagi.
Okay, selamat pagi Jo. Okay, while waiting for Associate Professor Jorayan preparing.
It is simpler and trivially we can find the rainbow coloring. And rainbow coloring is not a proper coloring like just proper coloring.
Floor is yours.
Okay, thank you very much for your introduction. And first of all, I would like to thank Professor Dafik for inviting me to give this talk in this conference. So I will first.
Combinatorics and graph theory and network topology that have invited me to join our prophet to join of this conference. Sorry.
First of all, I thank Professor Dafik and his group, second research group, for inviting me again in the 2020 for delivering a talk on graph coloring. I thank
Your attention, please. Well, ladies and gentlemen, welcome back to the Q&A session of Day 2 in International Conference on Combinatorics, Graph Theory and Network Topology, ICCGANT 2022. Now we come to our third invited speaker, which will be delivered by Ibu Kiki Ariati Sugeng. Hello, Ibu Kiki, are you with us? Okay, Assalamualaikum warahmatullahi wabarakatuh. Welcome back to the third session of ICCGANT 2022. Now we will have Ibu Dr. Kiki Ariati Sugeng as our third invited speaker. Hello, Kiki, can you hear our voice?
Yes, I can hear you. Thank you.
Okay, before deliver the talk, let me read a short CV of Ibu Dr. Kiki Ariati Sugeng. Ibu Kiki Ariati Sugeng is a senior lecturer in the Department of Mathematics, Universitas Indonesia, and she got her master degree from Institut Teknologi Bandung. And Bu Kiki got her PhD degree from the University of Galaran. Now, she is a reviewer in many reputable journals, and she also former president of Indonesian Combinatorial Society. She has about 105 Scopus document with H-index 11. For Bu Kiki Ariati Sugeng, time is yours.
Okay, thank you for the introduction. So, good day, everyone. I would like to thank to Professor Dafiq and the team to invite me to be the one of the speaker in this seminar. And also, I would like to say hi to Professor Dafiq and Professor Lamin. Yeah, both of you has what is Professor Imran and Dr. King Kardas like say their warm regards to both of you. So, yeah. Okay, so I would like to start my presentation. So today I would like to share the topic about local anti-magic labeling. I know that this topic is very popular in Jember because like many results come from this group. So yeah, I think it's better to start. There are like Professor Slamin already mentioned, we have like many labeling, this magic and anti-magic labeling, vertex X total anti-magic labeling, and then we can like find variation of anti-magic labeling, and also the late it it can be called latest, but not like very late. There is a new variation that we call local anti-magic labeling and super local anti-magic labeling. So I think I would skip a little bit about this one because Professor Slamin already mentioned about this. So this introduced by Sedlacek in 1963, but it needs like a long time to people get interest, and then until the late 1990, there are like lots of people interest in this what is topics with all the variation in labeling. So we know that Gallian survey already like collecting, I don't know the status right now, maybe like more 1,000, maybe 2,000, like all result that can be found in the internet. But not every result can be found in the Gallian survey, because like we know that there are also many results in other language like Indonesian, so they cannot like find what is the keyword for that. Yeah. For the edge magic total labeling, we know that there are like famous conjecture that all trees have edge magic total labeling, and also all trees have super edge magic total labeling. Until now, the conjecture are still open, so we still like have the opportunity to work in this area. Okay, so after 1963, so the printed proof that somebody talk about magic and anti-magic labeling is in Harsfield and Ringel in 1994. In this book, there is a definition about the anti-magic. Yeah, so if like the label called magic, it means that the valuation or the weight or whatever we want has the same numbers k. Yeah, so that we call it magic constant. For anti-magic, it can be vertex anti-magic or edge anti-magic. So in this case is vertex anti-magic. Yeah, it means that we label all the edges from 1 to 3 until number of the edges, and then we calculate the weight of the vertices. So as the example here in path, we have label 1, 2, 3, and 4, and we can calculate the weight of the vertices. This one is 1 because this is the sum of all the label of the edges. For V0, it will be 4 because it's 1 plus 3 and so on. And also, if we look at the star, we know that every leaf has the same weight with the label of the edges, because this is only vertex with 1 degree. And the the center will have the biggest number. Yeah, in this case is 36. So we know that for the anti-magic labeling that first introduced by Harsfield and Ringel, we try to find the way for labeling the edges such that the vertex label are all different. And the conjecture is every connected graph different from K2 is anti-magic, and every tree different from K2 is anti-magic, and these two conjecture are still open. Because like there are many people work in the magic and anti-magic labeling, so there are like some books special for these topics already published. The first one is from Martin Baca and Mirka Miller, Super Edge Anti-Magic Graph. The second one, I think this is the first one, yeah, from Alison Marr and Wolbolis. The title is Magic Graph. And the last one is Magic Anti-Magic Graph. This is from Baca, Miller, Jorayan, and also Semanikova and Venovsikova. The next one from Chartran, Egan, and Zhang. This is more general, yeah. So it's not only magic and anti-magic, but also the other labeling. Yeah. For the anti-magic labeling, we have like some variation. like before, we label the edges such that all the weight are different, but we can like make it a little bit strict. So the difference will be a difference by D. So it's not only all different, but it's like the weight will be A plus D, A plus 2D, and so on. And then we can like have, this is the example, the 4 variation. This is depends on and what kind of weight that we have. The first one, we label the like ADH anti-magic vertex labeling, mean we label the vertices, and then we calculate the weight of the edges. Yeah. And the second one, we label the edges, and then we calculated the vertex. The total one means that the label we put on the edges and vertices, and the weight can be in vertex or edges. Sorry. And the last one, there is additional word in here, super, means that the label, the smallest label 1 until number of vertices is used for the vertices. We also like have variation for magic anti-magic labeling with the first one is distance magic anti-magic total labeling. So when we calculate the weight, it means that we also consider the distance between one vertex and the others. And also we have D distance magic and the magic total labeling, means the distance can be more than one. For distance magic and the magic total labeling, it means that the distance is 1. So we calculated, say, like all the vertices in the neighborhood, but for this one, it can be more than just neighborhood, but second neighborhood, or like it depends on the D that we choose. Okay. So the one that I would like to share is about vertex and the magic total labeling, means that the weight is in vertex can be super, because like if we put the smallest label, it's for all the vertices. So this is the example. AD means that the weight of the vertex weight will be difference by D. So A plus D, A plus 2D, and so on. Its labeling means that the label here is in H, but if this is total, it means that we label the H and vertices. For this one, because we only like have vertex and the magic H labeling, so the example here we can see for these vertices, the sum label of all the edges that incidence to this vertex is 4 plus 11 plus 3, so it means it's 18. And we can see that all the vertices here has different label, but it's not only different label. We can see this is 9, 12, 15, 18, 21, 24, 27, and 30, and the difference between them is 3. So this one is 9,3 vertex total, vertex H labeling, vertex and the magic labeling. Sorry. Okay. So this is the this. So this one is the definition for vertex magic on anti-magic labeling. We have the function or label for vertices and edges, and we assign the label is 1, 2 until number of vertices and number of edges here. And the weight of the vertices is the label of the vertex X plus all the label of edges that incidence. If the number is K, it's a constant, so we call it vertex magic total labeling. If the weight are different, that we call it anti-magic. And if the label of the vertices is 1 until n, we call it super vertex magic total labeling or super vertex anti-magic total labeling. So it depends on the kind of label that we want to use. Okay. For super vertex magic total labeling, there are like some it's not a characterization, but there is like some properties that we will have for, say, the regular graph R. Then G of order n can be have supervertex magic total labeling. The n and r should be have a opposite parity, and also the number of n, it's if it's 0 modulo 8, then E will be 0 modulo 4. If n is 4 modulo 8, then E should be 2 modulo 4. There is like some requirement that if you want to like label the regular graph, we need to check this property first. For cycle, we only have supervertex magic total labeling if n is odd. But if we delete the super on the vertex magic total labeling, then it works for Cn for n odd and even. Okay, for trees we cannot label the supervertex magic total labeling.
Kan cycle Cn, n-nya odd kan yang punya magic yang
Iya. Yes. Any question? Yeah, so for cycle, it's only n odd that have super vertex magic total labeling. For n even, we don't have the super one, but we still can have vertex magic total labeling. For anti-magic total labeling, there are like lots of results. This is just some example. So start from the very simple graph like path, cycle, and then going to a more complicated one like generalized Peterson graph, prism, complete graph. Complete graph. The conjecture is for D equal to 0 and even also like have the labeling. Okay, sorry. Something wrong. Okay, so we also like have some property that we can see. Some of the family of graphs cannot like have supervertex anti-magic total labeling. Like this is like the example. So for this kind of labeling, we cannot say that all graph can be labeled, yeah, by supervertex anti-magic total labeling, because like we can prove that these classes of graph cannot have what is the supervertex anti-magic total. Okay, so we start with the anti-magic total labeling in 90, and then Arumugam in 2017 introduced local anti-magic vertex labeling, and then the group from Jember introduced local anti-magic total vertex labeling in 2018. And also super local anti-magic total labeling. This is like in the same paper. Yeah. And the next one is the local super anti-magic total vertex coloring of some Bill related graph. There are like still more results after 2020, like Professor Slamin already mentioned. There is like some new result in 2021 and 2022. I haven't got any chance for like adding or like complete my my data about that one. Yeah, but I know there are like lots more than what we list in this slide. So what is local anti-magic labeling? So local anti-magic labeling means that we label the ages, yeah, almost the same with the previous one, with 1 to until number of ages. The difference is the weight, yeah. So before we have the weight will be different for all U and V, yeah. But for the local case, this is only for the U and V that adjacent. Yes. So if it's not adjacent, it can be the same. Okay. So we will try to find the minimum number of the weight that are different, that we call it by Kaila. This is the minimum number of colors here, because like the weight can be seen as the color for this one. So here are some known result that like path for n greater or equal to 3, the Kaila is equal to 3, the total one is also equal to 3, the super local anti-magic total vertex labeling still have the range from 3 to 4. And also we have cycle, we have wheel, we have complete bipartite K to N and KMN. There are like various people work on this area. And also there are also who work in tree, fan, a star, kite, cycle with pendant, and the gear. When we check at that time, there is one in a local anti-magic total labeling. So they have Lat is equal to 3, Kai slat is equal to 3, but we still haven't find the Kaila. So that's why we want to look at the local anti-magic vertex labeling for the gear graph. So gear graph is the wheel, yeah, but we add like one more vertices between the vertices in the cycle. So like this. So this is like we originally have like a wheel with 3 vertices in here, but on the edge in the cycle we add like one more here, the 3. So we call it the gear graph. The label will be like this. Sorry, it's not consecutive. Yeah, just finish everything. Sorry about that. Okay. So like the 15 in here, so we label the edge between the center to this 15 is 1, and then 5 and 9. And if we calculate, this is 15 and this is 11. And here we it should be 4 in here. So we can also like have a weight 15. This is like the coloring. So the coloring definition, we can like use the same color as long as the 2 vertices are not adjacent. So this is also like we can like have the same weight, 15 in here, 15 in here, and 15 in here, as long as it doesn't adjacent each other. Yeah, but if adjacent, this is like 15, so we have a different color here, 11, and this is 6, and this is 17. This is the example for n equal to 3. And the other one is example for n equal to 7. We can do the same here. And we have all 13. Yeah, it's okay because it's not adjacent. And then we have 21 in 3 places. And the next one is 35. Yeah, so we have 21, one color, and then 28, second color, 33, like third color, 35 is the fourth color. Yeah, so we only need 4 color in the in this case of the gear. So the lemma, we know that the upper bound of or Kaila of the GN is equal less or equal to 4. This is for n equivalent with 1 modulo 2. And the proof is we need to find the formula for label of edges. This is the label of edges for the center to other vertices in the cycle. And also we need to find the label of edges PI-UI. And the next one, UI to VI plus 1. So, and the last one is UNV1. It's only one label in there. So we will have something like this. And then we can calculate the WC, this is the center, is equal to n over 2 times n plus 1. And the label of VI will be like this, and UI, it will be 3n or 5n, depends on its the I is odd or even. So we can see that the label here are 4, but this is just to show the upper bound. So for proving this case, we need to show the lower bound by the lemma, and then upper bound by constructing the label. And then if they are the same, we can see what is the number, yeah. For this one, for n equivalent 1 module 2, sorry, the lower bound is equal to 3. I will skip the proof. And the theorem, the construction, I mean, we only like have 4, so we cannot say cannot, yeah. At this time, we still cannot do to prove that the radius of the 4 or equal to 3 or 3 is impossible. So we still like have the range in here. The Kaila for the gear graph is in between 3 and 4. Okay, this is the example. Of the 3 color, I think, yeah. This one is for 3 colors. Sorry, this is also 4. And this, so the case, it will be divided by several case of n, yeah. For n even is 0 modulo 4 or 2 odd, yeah. I will skip the proof for this one. The techniques are similar. So this is like the overall of the label and also the weight. We can see that the weight is equal to 4 different weight. Yeah. So the what is the color or Kayla is less or equal to 4. Yeah. Okay. And then this is the lower bound. Because we have the lower bound is equal to 4, and the construction also we have the what is the color less or equal to 4, then we can see that for n even, the Kaila will be equal to 4. Yeah, so we have 2 different results. The next one that I would like to share to you, the first one is with the work with my students that already published in the proceeding. The next one is I work with other students and also collaboration with Budeni Silaban and Butita Mariati. And also for with the Libor project. This one is already published in Electronic Journal of Graph Theory. So the original definition is not defined by ours, but it's defined by the Jember Mafia. So Butri et al. In 2018. The local anti-magic vertex introduced by Arumugam, but Butri et al. Introduced the total one. Yeah. So the label is for vertices and edges, and the weight will be the same, and we can check that the weight between 2 vertices that adjacent each other should be different. This is the example. Yeah, so we have like 4 here, 5, 4, 5, and 2. So for the P5, we have the Kaila is equal to 3, but this is because it's total. So this is also Kaila. Yeah. And for the star, we can see that we have 17 in here, all for the leaves, and 36 for the center. So we only like need 2 colors, 17 and 36 for S8 or star with 8 leaves. Okay. So what we are working in here is the super. Yeah. So in the previous papers, they also like some of them like do the super labeling, but without mention this is the super super case. Yeah. But in this paper, we state that we are working on the super cases. It means that the label of the vertices will be 1, 2, 3 until number of vertices. So this is the example. If we don't use the super one, so we can see here, we have 1 and 2 for edges. Yeah. Then where is the 3? So this is 1 and 2. 3 in here also for edges, but 4 for vertices, 5 for vertices, 6 for vertices, 7 for vertices, and so on. But we have chi-lat is equal to 2. So this is also total, but it's not super. But if we change the label to super case, so we can see here, 1 is for the leaf is here. This is 2, and this is 3, 4, 5, and this 6. 7 is in the middle, the blue one, 8 and 9, and then 10. So all 10 labels, the smaller one is used for all the vertices. The next one is 11 for edges. So this is 11, and we have here. Okay, so this is 11, right? And then 12 in here. 15, this is 14, this is 15, 16, 17, 18, 19. Yeah. So after 10, all the labels is used for the edges. And the color, we have 17 in here. So 17 has color red in here. This is also 17. And this is also 17. So all the leaves have weight 17. If 17s we put color, we put like example in this graph is red. And in the center, this is 64, yeah. And the others is 53. So because we changed the label to the super case, we have a bigger color that we need, yeah. So for chi-slat is equal to 3. So we cannot have 2 anymore. In 2019, law like give theorem that every graph has a vertex superlocal anti-magic total labeling. Yeah. So we see in this paper we see the case for 3. So and also we success to characterize when the chi-slat is equal to 2. Yeah. So chi-slat like in the previous example. We have a 3, right? But if we try to find or to check what is the graph that has chi-slat 2, then we can prove this is for star. Yeah, and also for star, we already mentioned before, the color is 2 for the center and for the leaves. Yeah, but it can be generalized for any star. We can like have 2 colors, and if we have 2 colors, the 3 should be star. Okay. Then because like we already find the characterization that the chi-slat will be equal to 2 only for star, then if we have another 3 is not the star, then the chi-slat should be at least 3 in here. Yeah? Because if it's 2, then we will go to this one. So we will have star. Okay, how's about path? Path looks so easy, but we only can find the chi-slat is in the range in here 3 and 4, but this one is if I'm not mistaken, this one is what you call it, So we can like have Pn with the chi-slat equal to 3, and also we can find the Pn is equal to 4. In this example, we have the color green here is for 14, the red is for 26, the blue one is for 24. So we have 3 different colors for P7. The next family of graph that we check is that we call it shrub. Yeah. So this is the example of shrub. And we can prove that the chi-slat, the color of the shrub for like every M and P that has fulfilled the requirement, it will be equal to 3. So for this example, we can have a red color that is 23, the blue color, the weight is 68, and the green color is 148. We also like can show so if like the first we already characterized, if chi-slat is equal to 2, then it should be star, right? How's about 3? So we can see the example of path that have a chi-slat is equal to 3. And how's about the n equal to 4? Is there any graph in this paper is 3? Yeah, is there any 3 that has chi-slat equal to n? So we can construct the 3 something like in this picture, that we will have the 3 that we construct, the chi-slat will be equal to 6. So for this one, we have the red color. Sorry, it's this is should be 50, 60, yeah, 60 for the leaves, and then 155 here, and 185, 343, 373, and 830. So the construction we can see, we start from the maybe we can call it 2 leaves in here, yeah, and then we add like 1 more, so we can like make it bigger, can be the same, but the structure of the caterpillar will be like bigger and bigger. So we cannot like have the 3 with the chi-slat is equal to n if we have like I mean maybe there is the 3, but the construction it doesn't work. If like we have here we have like 4, and this is 2, and then 5, and so on, yeah. So it has to be the number of the leaves will be like growing up. And this is the other example for the construction. So that's it. Like this is like some references that we use. And thank you for your patience to listening to me. Okay, thank you very much.
Okay, thank you very much for for the talk about the anti-magic labeling, especially if for the audience here who want to ask question, please welcome.
I think there is no question because like many people there already work in this area, so they already knows about what is it.
Yeah, okay, once again, maybe any question? If you want to ask to Ibu Kiki, you can write your question in the chat box, or you can use the raise hand feature in the Zoom chat. The question? I think it's clear enough, Ibu Kiki.
Okay.
Okay, thank you very much, Ibu Dr. Kiki Ariyanti
Thank
for
you
the
very much for
session. Thank you for joining the International Conference ICCGANT 2022. I hope that your talk is can be what is that? You
can be better, yeah.
Okay, thank you very much. Please give a round of
Okay,
applause
thank you
for
everyone.
Okay, well, ladies and gentlemen, now we go on to our last invited speaker, which will be delivered by Mohana Priya from the Combinatorics Art and Science College. But before we go on to the presentation of our invited speaker, let me read a short introduction about Dr. Mohana Priya. Dr. Mohana Priya is the assistant professor in the PG and Research Department of Mathematics, Combinatorics Art and Science College in India, and she got the MSc degree in mathematics from the Combinatorics Art and Science College, and she got the PhD degree in the mathematics also from the Bharatya University, India. Dr. Mohana Priya research interest is in graph theory, graph coloring, domination of graph, and also graph labeling. Now, let me invite Dr. Mohana Priya to come to the stage. For Dr. Mohana Priya, time is yours.
Selamat siang dan terima kasih. At the outset, I would like to thank the management of Combinatorics Arts and Science College for giving the permission to attend this wonderful conference, and also Honorable Rector and Vice Rector of Jember University, and my special gratitude to the Professor Dafik for inviting me for this 6th International Conference in Graph Theory. So today I'm going to deliver my talk on topological indices in graph theory. As our one of the keynote speaker, Logesha, has given the outline about the indices, some of the indices. So here I am going to talk about the Sombar index, which we have given a study on that. So this is my outline. My slides are moving. So these are the outline of my talk. That is, I'm going to give some introduction about the topological indices and various type of topological indices. And I'm going to talk on the Sombar index of using some graph operations for topological indices. And finally, I'm going to talk on the application of topological index. So as our Logesha sir mentioned that suppose a molecule is composed of n atoms. For any two atoms, we can have decided two statements. In a molecule, there is the chemical bond between the two atoms, and the another statement is that in a molecule there is no chemical bond between the two atoms. So the totality of information about the mutual connection between the atoms in a molecule has been represented by an pictorial way, that is called it as a molecular graph. So the molecular property, one must convert the information contained in a molecular graph in a numerical characteristic. So every number is uniquely determined by a graph is called a graphical invariant. So the topological index, as I mentioned, is a type of molecular descriptor that calculates the numerical values associated with the graph and characterize its structure. So it is as characterized based on degree-based topological indices and distance-based topological indices and counting-related topological indices. But degree-based indices has a wide application in the field of chemical graph theory. So generally, we have the formula for topological index of a graph, that is summation Eij, which belongs to the edge set of G, the function of the degree of Vi and degree of Vj. That means f of x comma y is equal to a function of y comma x. So here there are some types of topological indices in which the first index is Wiener index. The Wiener index of the graph G was denoted by W of G, so which is defined as the sum of the distance between the pair of vertices, that is W of G equal to summation over U comma V, which belongs to the vertex of a graph, the degree of the distance between the pair of vertices U and V. So here I'm considering a graph, star graph. That means S5, V1, comma V2 plus V1, comma V4, V3, the pair of vertices V1 and V2, we have the distance 1, and the distance between V1 and V3, we have the distance 1. Likewise, adding up all the distance between the two vertices is 16. So the Wiener index of the path, if I consider a path with 3 vertices, we have the Wiener index is 4. Likewise, the path with 4 vertices, we have the Wiener index is 10. The path with 5 vertices, we have the Wiener index 20. So generally, we can write the Wiener index of the path Pn is equal to n cube minus n by 6. Likewise, we can have many results which was already found by the authors. Next, we are going under Harare index, which is also a distance based. So the Harare index of G is a reciprocal of Wiener index, that is h of G. We will denote the Harare index is h of G. So h of G equal to summation U comma V belongs to V of G equal to 1 divided by the distance between the pair of vertices. Here I'm considering the graph, again I'm considering the graph path. So the Harare index of the path Pn is summation I equal to 1 to n minus 1. N minus I by I is the result for the path. So likewise, here I'm giving the example of the S5. So the reciprocal of the pair of vertices V1 and V2 is 2. Likewise, I'm taking the every pair of vertices distance and taking the reciprocal of that. We will get the Harare index of S5 is 7. Next, the very interesting and application of Zagreb index, which is mentioned already. That is the sum of the squares of degree of any vertex U of a graph G is the first Zagreb index, which is denoted by M1 of G. So the first Zagreb index is defined as M1 of G equal to summation U belongs to V of G, that is the degree of the vertex U square. So here I am giving the example for the cycle with vertices 6. M1 of C6 is nothing but each vertex degree is 2. So by adding up all the degree of the vertices and squaring up, so 4 plus 4 plus 4, we have 6 vertex. So that is equal to the value is 24. The index value is 24. So next, the second Zagreb index, that is nothing but the sum of product of the degrees of any two pair of vertices U and V of a graph is called a second Zagreb index, which is denoted by M2 of G. So it is defined as summation U comma V, which belongs to the edge set of that graph, then the degree of the first vertex into the degree of the second vertex. So here I'm taken the example for the cycle graph with the vertex 6. So the degree between V1 and V2, the degree of V1 is 2 and the degree of V2 is 2. So by taking the product of those two vertices, 2 into 2, 4. So by adding up all the pair of vertices product, so we will get the first Zagreb index as 24. So likewise, we can extend our result to the other families of graphs. Next, atom bond connectivity, which is the main application in chemical graph theory. So we call atom bond connectivity as ABC index. The ABC index of a non-trivial graph G is denoted by ABC of G, is defined as summation over U. V belongs to the edge set of G, that is square root of the degree of the vertex U plus degree of the vertex V minus 2 divided by the product of the degree of vertex U into the degree of the vertex V. So here the example is, so here I'm considering S5, that is star graph with 5 vertices. Here we have 4 edge, so 4 into the square root of the degree of that vertex V1 is 4. The rest of the vertices we have the degree 1. So 4 plus 1 minus 2 divided by 4 into 1. So the result is the 2 into root 3. That means atom bond connectivity for this star graph result is 2 root 3. So next we are going to the harmonic index. The harmonic index of a graph is denoted by HI of G, which is defined as the fraction of 2 divided by the sum of the weights of all the edges UV of G. So HI of G equal to the summation UV belongs to the edge set of G, that is 2 divided by degree of vertex U plus degree of the vertex V. So here again, I'm considering the star graph with 5 vertices. So in star graph with 5 vertices, we have 4 edge. So 4 into 2 divided by the degree of the vertex V1. V1, we have the degree 4 and the rest of the vertices, we have the degree 1. So 4 into 2 divided by 4 plus 1, that is 8 divided by 5. The harmonic index of the star graph S5 is 1.6. Likewise, we can extend the result to the rest of the special graphs. Randic index. So the Randic index is denoted by R of G, which is also known as the connectivity index of a graph G, which is defined as summation of U, V belongs to the edge set 1 divided by the square root of the degree of the vertex U into the degree of the vertex V. So here I have taken the complete graph for this Randic index. So here R of K6 equal to, here we have 15 edges for this graph. So 15 into 1 divided by the square root of the degree of the vertex V1 into the degree of the vertex Vj. So here I'm considering the degree of the vertex V1 is 5. The rest of the vertices also having the degree, each vertex of degree 5. So 5 into 5 is 25. Root 25, the value is 5. So the value, the Randic index of the complete graph is 3. Next, the forgotten index. The forgotten index is nothing but we call third Zagreb index, as I already have mentioned about the first Zagreb and second Zagreb. Likewise, this is a forgotten index. The forgotten index of a graph G is denoted by f of G. So here the forgotten index is mentioned, the summation over U belongs to the vertex set of G, degree of the vertex cube. So here I have considered an example for the cycle with vertices 6. So each vertex of degree is 2. So the degree of vertex, first vertex cube is 8. Second, likewise, 6 vertices cube is 8. So the total of this degree is 48. That means the forgotten index of the cycle with 6 vertices is 48. Sum connectivity index. So sum connectivity index of a graph is denoted by chi of G. So the chi of G is nothing but the summation UV belongs to the edge set is 1 divided by the square root of the degree of the vertex U plus degree of the vertex V. So here again I am taking the graph cycle with 6 vertices. So totally we have 6 edges. So 6 into 1 divided by each vertex of degree 2. So here I am considering the degree of the vertex 1 is 2. The rest of the degree of the vertices is 2. So 2 plus 2 is 4. The square root of 4 is 2. So the sum connectivity index for this cycle graph is 3. So the reciprocal sum connectivity index of a graph G is denoted by RSC of G, which is defined as summation UV belongs to the edge set of G, that is square root of the degree of the vertex U plus degree of the vertex V. So again, I'm considering the cycle graph for as an example for reciprocal sum connectivity of a graph. So here totally we have 6 edge in a cycle. So 6 into the square root of the degree of the vertex V1 plus degree of the vertex Vj. Here the degree of vertex V1 is 2. The rest of the vertices have the degree 2. So 2 plus 2 is 4. So the reciprocal sum connectivity index for cycle C6 is 12. Next, we are going to see about inverse degree index. Inverse degree index is a vertex degree based graph. As I mentioned, we have the topological indices which distance based, degree based and connectivity based. So here the inverse degree is a vertex degree based graph invariant. This is defined as ID of G equal to the summation of U belongs to the vertex set of G is 1 divided by the degree of U. So here I am considering the complete graph with 6 vertices for the inverse degree index. That means we have 6 into 6 vertices. So we have I am having 6 into 1 divided by each degree of the vertex is 5. So 6 into 1 by 5 is 1.2. That means inverse degree index of this complete graph is 1.2. Next, Sombar index. We have published 3 papers. We are going to publish the 3 papers in Sombar index by the collaborative work with Dafik sir. So the Sombar index is SO of G is a geometric interpretation of degree radii of the edges for a graph G is defined as SO of G is nothing but the summation UV belongs to the edge set of G is into the square root of degree of the first vertex square plus degree of the second vertex square. So here again I'm considering the Sombar index for the complete graph with 6 vertices. So totally we have 15 edges in a graph. So 15 into the square root of each vertex of degree is 5. So 5 square 25 plus 5 square is 25, the root 50. So the root 50 can be written as 25 into 2. So 15 into 5 root 2. So 75 root 2 is a Sombar index of the complete graph with 6 vertices. So this is our work on Sombar index of M shadow graph of some graph. So as I mentioned, the Sombar index of a graph is defined as xi, xj belongs to the edges set. Then the square root of the degree of the first vertex, xi square plus degree of xj square. So this new topological invariant is applied in the area of chemical graph theory. In this paper, we have investigated the Sombar index of M shadow graph with path graph, cycle graph, ladder graph, and tadpole graph. And also we have concluded that the Sombar index of M shadow graph of any finite complete connected graph, we have the Sombar index of the graph into M cube. So the shadow graph, first we are going to define about the shadow graph. The shadow graph is nothing but is a simple connected graph which is obtained by taking the two copies of the graph, that is G dash and G double dash, and joining the each vertex of G dash to the neighbors of the corresponding vertices of in G double dash. Similarly, M shadow graph is denoted by dm of G, is a graph which is obtained by taking the M copies of the graph like G dash, G double dash, and up to G M copies, so G of M. And then joining each vertex of UI with the neighboring vertices of the corresponding vertex Vj, which is belongs to Gi plus 1, Gi plus 2, up to Gm, for J varies from 1 to M. So this is a result. Let Kn be a complete graph. Since a complete graph has a maximum degree, so let Kn be the complete graph of order n, and Kn bar is it complement of that graph, which is an edgeless graph. Then for any graph G of order n, then the Sombar index of Kn is a lower bound for Sombar index of a graph less than, and the upper bound for that Sombar index is Sombar index of the complete graph. This equality holds that G is isomorphic to Kn bar. That means the complement of complete graph, or G is isomorphic to the complete graph. Then we can say that Sombar index of Kn is 0. Then the Sombar index of Kn is n into n minus 1 by 2 divided by root 2. So the Sombar index of the graph varies from 0 to n into n minus 1 square divided by root 2. So the results which obtained for the path graph is, for a path graph Pn, the Sombar index is given by root 2 for n equal to 2, and for other cases 2 root 5 plus 2 into n minus 3 into root 2. So here the lowest graph is Sombar index of the path is less than or equal to Sombar index of G less than or equal to Sombar index of Kn, which is our observation. So here we have given the theorem for M shadow graph of path graph. So Pn is be the path graph of order n. Then the Sombar index of M shadow graph of path graph Pn is S scope of a Sombar index of path with 2 vertices into M cube is the result for M shadow graph of the path. Then for other cases, Sombar index of the path into M cube is the result. Here I have given the proof for this theorem. Let the vertex set of the M shadow of the path is, we have considered as Vj dash, Vj double dash. For M copies, we have taken the vertex set Vj of M, where J belongs to 1 to n. Be the vertex set, where Vj or the vertices of M copies of the path Pn. The vertex of the first copy is adjacent with all other copies of the vertices. Since the M shadow graph of the path are constructed from M copies of the path, so the total number of vertices and degrees are given by, so the order of that graph is Mn, then the size of that graph is M square into n minus 1 respectively. The minimum degree of that M shadow graph of the path is M, and maximum degree is also M. So for M shadow graph of the path, For n greater than or equal to 3, the maximum degree is 2m. And by Goodman, he has given the result on Sombar index of G, that is summation by the definition, VIVL belongs to the edge set. Then the square root of the degree of the first vertex square plus the degree of the second vertex square. Then therefore, for the, here I have taken the two cases for n equal to 2 and for the other cases. So first, for the first case, n equal to 2, the Sombar index of M shadow graph of the path P2, we have an edge set of that graph into the square root of minimum degree of the path with first vertex, then the maximum degree of the path. So here the minimum degree of this path is m, while taking the square, m square plus m square. So totally we already, the edge set of the m shadow graph of P2 is m square into 2 minus 1. So m cube into root 2. So the Sombar index of the path with 2 vertices into m cube is a result. Then for the other case, there are 2 m square pair of vertices with both maximum and minimum. So here the result is Sombar index of M shadow graph for n greater than or equal to 3. The result is 2m square into the square root of the minimum degree of that M shadow graph of path square plus maximum degree of M shadow graph of path square plus n minus 3 into m square into square root of the maximum degree of M shadow graph of path with Vj square plus maximum degree of M shadow graph path with Vl square. So the result for this Sombar index of path into m cube. So likewise, we have taken the result on Sombar index of M shadow graph or for the complete graph. So first we will see the Sombar index of the complete graph result is n into n minus 1 square divided by root 2. Then for the cycle graph, the Sombar index of the cycle graph is 2n into root 2. So the M shadow graph of the cycle graph is Sombar index of the cycle into m cube. We predicted that Sombar index of the cycle, that is 2n into root 2 into m cube is the result. Next, we have taken the result for ladder graph. So the ladder graph, the Sombar index for the ladder graph is n into 3n minus 2 into root 2 for the vertex with 1 and 2, and the rest of the vertices we have the result 9n minus 20 into root 2 plus 4 into root 13. So the ladder M shadow graph of the ladder graph, the Sombar index result is Sombar index of the ladder graph with vertex 1 and 2 into m cube, and the Sombar index of ladder graph into m cube for the rest of the cases. Next, the result is extended to the tadpole graph. The Sombar index for the tadpole graph is 1 into root 10 plus 2 into root 13 plus 2 into n plus p minus 3 into root 2 for p equal to 1. Then for the rest of the cases, we have the result of Sombar index 1 root 5 plus 3 root 13 plus 2 into n plus p minus 4 into root 2. So we are taking the M shadow graph for the tadpole graph. Then the Sombar index of that tadpole graph, M shadow tadpole graph is the Sombar index of the tadpole graph into m cube for the p equal to 1. That means 1 into root 10 plus 2 root 13 plus 2 into n plus p minus 3 into root 2 into m cube is the result. Likewise, for other cases, we have the Sombar index of the tadpole graph into m cube. So from this, we have concluded that for any finite connected graph, the Sombar index of the M shadow graph of a graph is m cube into the Sombar index of that graph. So these are some of the product of the graph. We can extend the result for these type of product graphs. So first, Cartesian product of the two graph G and H. The vertex set of G and H is the Cartesian product of by combining the vertex set of G and vertex set of H. The two vertices U, U dash and V, V dash are adjacent in G and H if and only if either U equal to V and U dash is adjacent to V dash, or U dash equal to V dash and U is adjacent to V in G. This is also known as, we call it as a box product of a graph. So this is an example. Here I am considering graph, first graph G1 with path with 2 vertices and G2 with path with 3 vertices. By combining these 2 graphs, U1, U2, U1, V2, U1, W2, V1, U2, V1, V2, V1, W2. If U1 equal to V1, then we can make an adjacency with the U dash and V dash. Likewise, if U dash and V dash are equal, we can make an adjacency with U and V. So this is a Cartesian product of the path graph. Next, the tensor product of G and H. So here, first we have to take the Cartesian product of the vertex of graph G and vertex of graph H. So here, the vertices G, H and G dash, H are adjacent in G and H if and only if G is adjacent to G dash in G and H is adjacent to in H dash in H. So here, the tensor product is also called it as a direct product, Kronecker product, categorological product, cardinal product, relational product, weak direct product, or conjunction. So this is an example. Here I have considered path and cycle. So first I have taken a Cartesian product of these 2 graphs. That means x1, y1, x1, y2, x1, y3, x1, y4. And x2, y1 likewise. Make an adjacency if both the vertices of x and y is adjacent and x2 and y2 is adjacent. I have make an adjacency in the graph. So this is another example of tensor product of a path graph, 2 path graph. Here I have considered the 2 path graph. First, I have taken a Cartesian product of that graph, that is A1, A2, A3, A4, A5, likewise. Then I have make an adjacency if A is adjacent to B and 1 is adjacent to 2. So likewise, if A is adjacent to B and 1 is adjacent to 2, likewise. Next, the lexicographic product. The lexicographic product is a composition of the 2 graphs G and H. So here first taken the Cartesian product V of G and V of H, and any 2 vertices U, V and H, Y are adjacent in G if and only if either U is adjacent with X in G or U equal to U equal to X and V is adjacent with Y in H. If the edge relation of the 2 graphs are order relation, then the edge relation of their lexicographic product is a corresponding lexicographic order. So this is an example for the path graph, 2 path graph, that is U1 and V1. First, I have taken a Cartesian product. Then I have make an adjacency U1 and V1 and U2 and V2 and vice versa. So this is another example with a path graph with 4 vertices and path graph with 5 vertices. First, I have taken an Cartesian product of the graph. Then I have make an adjacency that V1 and V3, if it is adjacent, then we have to make an adjacency in this graph. And V1 and V3 of the second graph is adjacent. So we have to make an adjacency with that graph. So, and likewise, we can make an adjacency. Then the strong product. The strong product of the 2 graphs G and H is a graph such that the vertex set of G and H is the Cartesian product. First, we have to take the Cartesian product of the 2 graphs, and the distant vertices U, U dash and V, V dash are adjacent if and only if U equal to V and U dash is adjacent to V dash or U dash equal to V dash. The first 2 condition is just like a Cartesian product. And the third condition, U is adjacent to V and U dash is adjacent to V dash, like the tensor product. So the combination of the Cartesian product and tensor product, we combinedly call it as a strong product of a graph G and H. So this is an example. Here I have considered A, B, C, D as a first graph. Then I have considered a cycle with 4 vertices. So first I have taken the Cartesian product of the graph. Next I have taken an tensor product of the graph. So the combined graph, we call it as a strong product of G and H. Then the modular product. The vertex set of the modular product of G and H is the Cartesian product of V of G and V of H. Any two vertices UV and U dash V dash are adjacent in the modular product of G and H if and only if U is distinct from U dash and V is distinct from V dash, and either we have the two conditions, that is U is adjacent with U dash and V is adjacent with V dash, or U is not adjacent with U dash and V is not adjacent with V dash. This is an example graph with the two graph G and H. I am considering the path with 3 vertices. So here I have made an adjacency like Cartesian product. We have taken a pairs, that is A1, B1, A1, B2, A1, B3. Likewise, I have taken a pair of the vertices, and I have taken an adjacency like if A1 is adjacent with A2 as well as B1 is not adjacent with B3. So I have taken a, I have made an adjacency in the modular product. Likewise versa. Then semi-strong product. Here I have taken the condition of the vertex set of the semi-strong product of G and H is the Cartesian product of vertex set of G and vertex set of H, and two distinct vertices U, U dash and V, V dash are adjacent in G semi-product H if and only if U is adjacent to V and U dash is adjacent to V dash like tensor product, or U is adjacent to V and U dash equal to V dash. This is one condition which is taken from the Cartesian product. So this is an example graph with a path on 4 vertices and path on 2 vertices. This is another example. I have considered a path on 2 vertices and another graph with a cycle with 4 vertices. So the main application of this topological indices is to find the molecular structure of the graph in a chemical graph theory. So here widely we have used in the development of quantitative structural activity relationship in the chemical bonding, and in which the biological activity or other properties of molecules are correlated with their chemical structure. And QSAR, that means quantitative structure activity relationship, is a predictive model which are derived from the application of statistical tools correlating the biological activity of chemical compounds with descriptors representative of molecular structure and its properties. It is applied in these areas, that is risk assessment, toxicity prediction, and regularity decision, drug discovery, and lead optimization. So for example, extended topological atom indices has been applied in the development of predictive QSAR and QSPR and QSTR models. So thank you. We can extend this result for many special graph. If you have any queries, you can.
Okay, thank you very much for Dr. Mohana Priya for the talk. Now we go on to the discussion time. For ladies and gentlemen who are in the Zoom meeting or in this room who want to ask a question to Dr. Mohana Priya, please welcome. Any question? Once again, is there any question from the participant? Okay, I think there is no question, Doctor. Because maybe it's very clear about the topological in this graph theory.
Thank you so much for giving me this opportunity by Dr. David for giving me the lecture on the Sombar index of graph. So thank you for the participant for patient listening of my lecture. Thank you so much.
Thank you very much. Okay, well, ladies and gentlemen, let me read a short concluding remark from Dr. Priya Talk. Okay, topological indices are a type of molecular descriptor that plays a very vital role in the field of chemical graph theory, molecular topology, and mathematical chemistry. It is widely used in the development of the quantitative structure and activity relationship, in which the biological activity or other properties of molecules are correlated with their chemical structure. And there are so various applications such as in the risk assessment, toxicity prediction, regulatory discussion, drug discovery, and with optimization. Okay, once again, let's give a round of applause for Dr. Muhammad. Okay, well, ladies and gentlemen, this is the end of our second day plenary session in the International Conference on Combinatorics, Graph Theory and Network Topology, ICCGANT 2022. Me, as a moderator, would like to ask you apologize if there are many mistakes during this event. For the next agenda, I will give back to the master of the ceremony. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much to our keynote speaker, Professor Dr. P. Lokesa, PhD, Professor Dr. Andes Lamin, MCom, SG, PhD, Kiki Arianti, MSc, PhD, and Dr. Ohana Priya for the amazing presentations. Ladies and gentlemen, please give applause for our today's keynote speaker.
Baik, kami sampaikan terima kasih kepada pembicara tamu kita, Profesor Dr. P. Lokesha, PhD, Profesor Dr. Andes Lamin, MCom, SG, PhD, Ibu Kiki Arianti, MSc, PhD, dan Dr. Ohana Priya, dan juga kepada Ibu Robiatul Adawiyah, SPD, MSc, sebagai moderator.
Ladies and gentlemen, before we entering the last agenda, we still have a certificate awarding for our keynote speaker and moderator.
Hadirin sekalian, sebelum memasuki agenda terakhir, kita memiliki sesi penyerahan sertifikat kepada para pembicara tamu dan moderator kita pada hari ini.
Firstly, we would like to invite our first keynote speaker in Zoom meetings, Profesor Dr. P. Lokesa, PhD from Vijaya Negara Sri Krishna Devaraya Ballari, India. Are you still there, sir? And the second, I would like to inviting our second keynote speaker, Professor Dr. Andes Slamin, MCom SC, PhD from University of Jember. And then I would like to inviting the third keynote speaker, Ibu Kiki Arianti, MSc, PhD from Universitas Indonesia. And the last one, I would like to inviting Dr. M. Hana Priya from Combinatorics Arts and Science College India to join with us in the stage. And I would like to invite Dr. Arika Indah Kristiana, SSC MPD, to give the word.
Pemberian sertifikat oleh Ibu Dr. Arika Indah Kristiana, SSC MPD. Disilakan.
Ladies and gentlemen, please give applause to our chairman. And for Dr. Lokesa, Professor Dr. Slamin, and Ibu Kiki Arianti will be represented by Professor David. Ladies and gentlemen, thank you very much, Professor David. Thank you very much, Bu Arika. Ladies and gentlemen, time goes so fast, and now we are entering our last agenda, that is closing and documentations. Please, to all participants in the Zoom meeting, to turn your camera on.
Hadirin sekalian, tidak terasa waktu telah berlalu. Kita memasuki acara terakhir, yaitu sesi foto bersama dengan seluruh partisipan. Kepada seluruh partisipan diharapkan menghidupkan kamera masing-masing.
And to all participants, offline participants, please come forward to the stage for documentation. Thank you.
Kami persilakan untuk seluruh partisipan untuk
Apa yang belum? Sudah semuanya ini. Oke, siapa yang mau foto dan tengkar bilang dulu? Sudah.
Thank you very much, ladies and gentlemen. Before we close this event, we would like to inform you, after this main event, we still have parallel sessions that will be held on 2:30 p.m. in Zoom breakout rooms. So please, all participants, do not leave this room. So please enjoy your break time and see you again at 2:30 p.m. in the Zoom breakout rooms.
Sebelum mengakhiri acara ini, izinkan kami menyampaikan informasi bahwa setelah ini akan ada sesi paralel yang akan dilaksanakan melalui Zoom breakout room pada pukul 14.30 WIB. Kepada seluruh partisipan diharap untuk tidak meninggalkan Zoom dan disilakan untuk beristirahat sejenak. Terima kasih.
International Conference on Combinatorics and Topology 2022. Let's close this event by saying hamdalah agenda.
Hadirin sekalian, marilah kita tutup dengan bacaan hamdalah bersama-sama.
Alhamdulillah. For the last, I do apologize and make a mistake. Thank you very much for your time and patience. And wassalamualaikum warahmatullahi wabarakatuh.